A time traveler arrives at a historic event. They do not intend to interfere. They only want to watch. They take careful steps to stay hidden. They believe they can observe the past without changing it, but their presence alone is enough to shift the course of history. This is the heart of the observer's paradox in time travel. The idea is simple. Even if a person does nothing, their existence in the past could influence events in ways they do not realize. Imagine a historian who invents a time machine. They choose to witness the signing of the Declaration of Independence. They dress in period clothing, remain in the background, and make no contact with anyone. They believe they are just another face in the crowd. But what if someone sees them and hesitates? What if one of the signers glances at this unfamiliar figure, pauses for a moment, and then changes a word in the document? That hesitation, that small change, could create an entirely different outcome. The historian did not speak. They did not act. But their presence altered history. A more extreme example could involve a journalist who travels back to witness the assassination of Archduke Franz Ferdinand in 1914. They want to see it exactly as history recorded, but their very presence might cause one of the bystanders to move differently. Perhaps a witness, startled by an unfamiliar face, shifts a few steps to the side. That slight movement could cause the assassin to miss or change the sequence of events that followed. World War I, a war that shaped the 20th century, might unfold in a completely different way. The journalist would never know how their observation changed history, but the effects would ripple forward in ways no one could predict. This paradox does not require the time traveler to act. It does not even require them to be noticed. The environment itself can react to their presence. Suppose a scientist builds a machine to go back and study dinosaurs. They step out of their time capsule and remain silent. They avoid touching anything. They do not interact with the animals. But their scent, their body heat, or even the displacement of air from their arrival could disturb a butterfly resting on a leaf. That small shift could lead to a predator missing a meal, a change in migration, or the survival of a creature that should have died. Over millions of years, that one disturbance could shape evolution in a way that creates an entirely new world. Even a passive observer can introduce change in less direct ways. A person standing in a field might cast a shadow that a passing bird avoids. That bird might have dropped a seed in one location, but now drops it elsewhere. A tree grows in a different spot than it originally would have. The tree shades the ground in a new way, changing which plants survive. Generations later, an entire forest stands where it never would have before. That minor shift could determine whether an ancient civilization thrives or fails. A time traveler, simply by existing in a place they were never meant to be, might redirect the course of history. The observer's paradox challenges the idea of passive time travel. It suggests that no one can travel to the past and remain neutral. It implies that history is fragile and that any change, no matter how small, will always have consequences. The traveler might believe they are careful. They might avoid direct interaction, but they cannot erase their presence. The mere act of observation guarantees that the past is no longer the same past they intended to see. The paradox also raises questions about knowledge itself. If a historian visits the past to verify an event, are they seeing the real history, or are they seeing a version of history altered by their presence? If a scientist records data from the past, can they trust their findings, knowing that their very act of observing may have changed what they measured? If a time traveler watches an event, how can they be sure they are not part of the reason it happened the way it did? In some interpretations, this paradox suggests that time travel to the past is impossible because history does not allow observation without interference. In others, it raises the idea that history is self-correcting, adjusting itself to absorb any changes the traveler might introduce. Some theories propose that any time traveler who goes back will only ever see a version of history that already includes their presence. If they were always there, then nothing actually changed. But if they were never meant to be there, their very existence might split time into a new branch, creating an alternate history that never existed before. The paradox becomes even more complicated when considering human psychology. If a time traveler watches a famous speech, Their silent reaction could influence the speaker's confidence. A glance, a nod, or a moment of distraction from an unknown face in the audience could shift the speaker's tone or choice of words. That subtle shift could reshape how the audience responds, altering how history remembers the moment. A speech that once inspired revolution might now fall flat. A message that once united a people might now go unheard. The traveler might never realize how their observation shaped the outcome. There is also the question of memory. If a person observes a key moment in history, do they bring back a memory of what truly happened, or do they remember the version of history that now includes their presence? If a historian takes notes on an event, do those notes reflect what was always supposed to happen, or do they now document an altered version of the past? Can anyone ever be sure they are witnessing the true past, or are they always seeing a version that has been touched by their own existence? The observer's paradox also raises ethical concerns. If a traveler knows they cannot observe the past without influencing it, should they go back at all? Even the best intentions cannot erase the fact that their presence creates change. A scientist studying the past might justify their actions by claiming the changes they introduce are too small to matter. But how can they be sure? If every action, no matter how minor, has a consequence, then even the smallest interference could lead to massive, unpredictable effects. A decision to observe might seem harmless in the moment, but could reshape history in ways that cannot be undone. There is no way to predict how a time traveler's presence might change history. A single breath, a misplaced step, or a moment of hesitation could be enough to alter the course of events. The traveler may never know what they changed. They may return to their own time and see a world that looks familiar, unaware that it has shifted in ways they will never recognize. The paradox does not require them to act. It does not require them to speak. It only requires them to exist in a time and place where they were never meant to be. A person steps into a time machine and sets the controls for 100 years in the past. Their goal is simple: to test if they can change history. They arrive in a bustling city square, blend into the crowd, and pick a random event to alter. Maybe they try to stop a stranger from boarding a train. Maybe they attempt to prevent a minor accident. But no matter what they do, events always seem to correct themselves. The stranger they try to stop takes another route and still reaches their destination. The accident they attempt to prevent happens in a different way. Every effort to change the past fails. They begin to realize that history resists alteration, as if events are locked in place. This is the core of the no free will paradox. The paradox suggests that if time travel to the past is possible, and the past cannot be changed, then free will might not exist. Every action taken in the past must have already happened, meaning there is no room for choice. The time traveler may believe they are making decisions, but if they successfully arrived in the past, then their actions must have been predetermined. They were always meant to be there. Their choices are part of a sequence of events that cannot be altered. This idea challenges the way most people think about time and decision-making. A famous example of this paradox appears in the concept of predestination. Imagine a person who receives a mysterious note telling them to go to a certain place at a certain time. When they follow the instructions, they accidentally cause the event they were trying to investigate. If they never received the note, they never would have gone. But the note itself only existed because they followed it. Their actions were not really their own choice. They were simply fulfilling a role that was always set in place. This paradox plays out in many fictional stories. A time traveler might try to warn people about a disaster, only to realize that their warning is what caused the panic leading to the disaster. A person might go back to save someone's life, only to discover that their intervention is what caused the person's death in the first place. If the past is fixed, then every attempt to change it is part of the timeline itself. No action is ever truly independent. To see how this paradox affects the idea of free will, consider an everyday choice. A person walks into a coffee shop and decides whether to order a latte or black coffee. They believe they are making a decision in the moment. But if time is fixed, then their choice has already been made. Every thought, every movement, every hesitation they feel has already happened. It feels like a choice, but it was always going to happen exactly as it did. This idea conflicts with how people usually think about time. Most believe the future is open, shaped by decisions made in the present. But if time travel exists and the past cannot be changed, then time is not a flexible path. It is a fixed structure. A person may feel they are choosing, but they are only following the one possible route through that structure. One way to think about this is through a recorded video. Imagine watching a security camera feed of someone moving through a building. They appear to walk freely, making choices at every hallway and door. But once the recording is complete, their movements cannot be changed. They went where they went. The idea of choice was only an illusion. If time operates in the same way, then every person's life is like a recorded video. They believe they are making choices, but they are simply moving through a fixed sequence of events. This paradox also raises questions about how decisions feel. If someone makes a decision and experiences doubt, does that doubt mean anything? If they change their mind at the last second, was that really a choice, or was it always the only thing they were ever going to do? Even if a person feels like they have free will, that feeling might just be part of the predetermined experience. Some philosophers and scientists argue that even in a universe without time travel, free will might not exist. They point to the way the brain works. If every thought comes from neurons firing in a specific pattern, and if those neurons follow physical laws, then each thought is simply the result of previous conditions. In that view, people do not actually choose their thoughts or actions. They only experience them as if they were making choices. Time travel adds another layer to this argument. If time is fixed, then every thought a person has ever had, every emotion they have ever felt, was already written into the timeline. Nothing can be different. If a person believes they can travel back and change something, they are mistaken. Their trip to the past has already happened. Their actions in the past are just as locked in place as everything else. This paradox also affects the idea of responsibility. If free will does not exist, then people do not truly control their actions. If a time traveler was always going to commit an action, then they had no way to avoid it. But that conflicts with the way most societies think about law and morality. People are held responsible for their choices because they are believed to have had the ability to choose differently. If free will is an illusion, that idea becomes difficult to defend. Some try to escape the paradox by suggesting that time splits into multiple branches whenever a decision is made. In this view, if someone travels to the past and changes something, they do not alter their original timeline. Instead, they create a new branch of time. But this raises other problems. If a person changes the past and creates a new timeline, what happens to the original timeline? Does it still exist? If every possible choice creates a new branch, then an infinite number of realities must exist. That idea solves the paradox of a fixed past, but raises more questions about how reality functions. Another way to think about this paradox is through a simple question. Imagine you are given the ability to travel 5 minutes into the past. You go back in time and see yourself standing exactly where you were 5 minutes ago. Now ask yourself, can you make a different choice than what you just saw yourself make? If time is fixed, the answer is no. Whatever you saw yourself do must happen again in exactly the same way. If you try to change it, something will prevent you, or your interference will turn out to be part of the event itself. Either way, your choices are not really your own. This paradox also makes people rethink the nature of reality. If time is unchangeable, then it is not just the past that is fixed. The future is also locked in place. If a time traveler from the future appears in the present and tells you what you are about to do, can you choose to do something else? If you believe in free will, you should be able to change your actions. But if time is fixed, then no matter how hard you try, you will still end up doing exactly what they predicted. For many, this paradox is unsettling. It suggests that every moment of life is already determined. It means that no matter how much a person struggles, hopes, or fights, their actions were always going to happen exactly as they do. If the past cannot change, then neither can the future. Every decision is just a step along a path that was already there. A man walks into a room and picks up a book. As he flips through the pages, he sees a note written in his own handwriting. The note tells him to go to a particular location at a specific time. He follows the instructions and arrives at an abandoned building. As he enters, he sees a younger version of himself standing in the middle of the room, confused. The older version of himself hands the note to the younger man and tells him to follow it when the time comes. Then, he leaves. The younger man looks down at the note and wonders where it came from. He recognizes his own handwriting, but he doesn't remember writing it. He follows the instructions just as the older version of himself did before. The cycle continues. The reverse causality paradox creates situations where an event seems to happen before its cause. It defies how people usually think about cause and effect. Normally, something happens, and that causes another thing to happen. If a glass falls from a table and breaks, the cause is the glass falling. The effect is the glass breaking. Reverse causality suggests the opposite. The glass breaks first, and then it falls. The order of events doesn't follow the usual pattern of time moving forward. Instead, the effect occurs before the cause. Imagine a scientist who invents a time machine. She wants to test it, so she decides to send a simple message back in time. She sets the machine to send an email to herself 1 week earlier. The next morning, she opens her laptop and sees an email from her future self. It tells her exactly how to complete the final calculations for her time machine. She follows the instructions, finishes her work, and eventually sends the same email back in time. The problem is that the email never had an original author. She never figured out the calculations on her own. The information exists in a loop with no starting point. This paradox appears in many forms. A musician dreams of a melody and writes it down. He later becomes famous for the song. Years later, he travels back in time and plays the melody for his younger self, who then writes it down and records it. The song has no origin. It exists because it was passed back in time, but no one actually composed it in the first place. Another version of this paradox happens when someone learns about an event before it occurs, leading them to cause the event itself. A man finds a newspaper from the future that reports a car accident at a specific intersection. He reads about the time and place and decides to avoid that intersection to stay safe. On the day of the accident, he takes a different route, but in doing so, he unknowingly causes a chain reaction that leads to the crash happening exactly as described in the newspaper. His attempt to prevent the event actually causes it. The accident happened because he tried to avoid it. This paradox challenges how time works. People usually think about time as moving in a straight line. First, something happens, and then something else follows. If a person drops a cup, it falls to the ground and breaks. The breakage comes after the fall. But in a case of reverse causality, the cup breaks first, and then it falls. That doesn't make sense in the usual understanding of time. The effect should not happen before the cause. Science fiction explores this idea in many ways. A classic example comes from stories where someone receives a warning about the future, but their attempt to change it causes the future they were trying to avoid. In one version, a man learns that he will be in a fatal accident. Determined to escape his fate, he leaves town and takes an unfamiliar road. Along the way, he gets lost and ends up at the exact place where the accident was supposed to happen. His decision to avoid the danger is what puts him in danger. The cause and effect become tangled. A more extreme example involves physical objects. Suppose a man builds a time machine and sends a hammer back in time to himself. He receives the hammer and then, years later, sends it back in time again. The hammer exists, but it was never made. No one forged it. It exists only because it was caught in a time loop. This scenario creates a logical problem. Every object must have an origin. If the hammer was never created, how does it exist? The same issue applies to information, people, and events. If something exists only because it was passed back in time, then it has no true beginning. This paradox becomes even stranger when applied to human actions. Imagine a scientist who builds a time machine. Before she tests it, a version of herself from the future appears and hands her the completed blueprints. She then follows those blueprints and builds the machine. Years later, she travels back in time and gives her past self the same blueprints. No one ever designed the machine. It exists because it was given to itself in an endless cycle. Reverse causality also appears in quantum mechanics. Some theories suggest that particles behave in ways that defy traditional cause and effect. A particle might seem to react to something that hasn't happened yet. Experiments in quantum physics sometimes show results that suggest future events influence the past. While this is not the same as time travel, it raises questions about how cause and effect actually work. The idea of events happening before their causes also appears in paradoxes like the Bootstrap paradox. In both cases, something exists without an identifiable origin. However, the reverse causality paradox focuses on how an event itself can be triggered by its own result. This can lead to infinite loops where causes and effects blend together in a way that doesn't fit traditional logic. This paradox forces people to reconsider their assumptions about time. If causes must always come before effects, then reverse causality should not be possible. But if time does not follow a strict linear progression, then cause and effect might not be as straightforward as they seem. In a world where reverse causality is possible, actions could be determined by future events rather than past ones. Someone might act because they have already seen the result of their action rather than the other way around. Time travel stories often rely on this paradox to create tension. A character might receive a warning from the future and then spend the entire story trying to change their fate, only to realize that their actions led to the future they were trying to avoid. This is a common theme in literature and film because it highlights the uncertainty of time travel and the possibility that events are predetermined. Some scientists argue that reverse causality cannot happen in reality because it would violate the fundamental laws of physics. Others suggest that under certain conditions, especially at the quantum level, events might not always follow the strict sequence of cause and effect. The idea remains controversial, but it raises interesting questions about how time functions. If reverse causality were real, it would have profound implications. It would mean that events in the future could shape the past just as much as the past shapes the future. A person could make a decision not because of past experiences, but because of something that hasn't happened yet. Reality would become much more complicated. This paradox makes people rethink their understanding of time, logic, and causation. It suggests that the universe may not operate in a simple, linear fashion. Instead, events might be connected in ways that are not yet fully understood. It challenges the assumption that the past determines the future and suggests that in some cases, the future might also determine the past. A time traveler makes a decision in the present, but that choice does not just affect the future. Instead, it changes something in the past. This is the core idea of the delayed choice paradox. It suggests that events in the past may not be fixed. Instead, they could depend on choices made much later. This kind of paradox challenges how people understand cause and effect. A simple way to think about this is with a story. Imagine a scientist in the year 2100 who has built a working time machine. She decides to test it by sending a message to a researcher in the year 1950. The message contains advanced equations that will help speed up the development of computers. The scientist sends the message and checks the historical records. She finds that the researcher in 1950 received the message, used the equations, and made breakthroughs decades earlier than expected. The entire field of computing developed faster because of this intervention. The problem is that the equations came from the future. The scientist only knew them because they were part of recorded history. But where did they truly originate? This paradox becomes even stranger when applied to personal decisions. Imagine a person who finds a mysterious journal filled with detailed knowledge about their own life. The journal contains instructions on how to invent a new technology, avoid mistakes, and even make the right career moves. Following the journal's advice, the person becomes successful. Many years later, they decide to travel back in time and leave the journal for their younger self to find. The problem is clear. The journal exists, but it has no clear point of creation. It was never originally written by anyone. It only exists because the person found it, followed its guidance, and then placed it back in time. Physics experiments suggest that something like this paradox could happen in reality. The famous delayed choice experiment in quantum mechanics shows that the behavior of particles can be determined by measurements made after they have already passed through a system. If the choice of measurement changes how the particle behaved in the past, this suggests that events at one moment in time can be altered by decisions made later. Now consider a different scenario. A man named Daniel has access to a time machine. He wants to win the lottery, but he does not have the winning numbers. He decides to travel into the future to find out which numbers win. Once he has the numbers, he returns to the past and writes them down on a piece of paper. He then buys a ticket using the exact numbers he recorded. After the winning numbers are announced, he realizes that they match what he wrote. But where did the numbers originate? If he only got them by looking at the future results, then there was no point where someone actually discovered them. They just existed in a loop. Another example is a musician who hears a song they love but cannot find any record of its origin. They assume it is an old song that has been forgotten. Later in life, they time travel to the past and play the song for a young composer, believing they are preserving an old classic. The composer then publishes the song, and over time it becomes famous. The musician in the future hears the song again and repeats the cycle. But if the song only exists because it was passed between the future and the past, who originally wrote it? These examples show how decisions made in the present could determine what happened in the past. They also highlight a key problem with time travel. If events can be changed based on future choices, then there is no fixed timeline. Instead, reality could be shaped by decisions that have not yet been made. The paradox also raises questions about free will. If the past is determined by future choices, then how much control does a person really have? If a time traveler decides not to send a message back in time, but historical records show that the message was received, then something must happen to force the traveler to send it. Does this mean that their choice was never truly theirs to make? If a scientist plans to send information to the past but then changes their mind, does reality shift to prevent that change? Some interpretations of time travel suggest that the universe must always be consistent. This means that any action taken in the present must align with what has already been observed in the past. If a future traveler sees a historical event happen a certain way, then no matter what they do, they cannot change it. This would mean that even if someone thinks they are making a free choice, they are actually following a predetermined path. Other interpretations suggest that the past is flexible and that each change creates a new timeline. In this view, the moment a time traveler makes a choice that contradicts the past, a new reality is created where their choice becomes the new history. This raises even more problems. If each choice creates a new timeline, then reality would split endlessly. Each version of events would exist separately, leading to an infinite number of possible outcomes. Now consider another scenario. A woman discovers that a famous historical event happened because of a mysterious message received in the past. She learns that the message helped prevent a disaster. However, when she researches the event, she realizes that there is no record of who sent the message. Years later, she gains access to a time machine and decides to send the message herself. She knows that the message must exist in history because otherwise the disaster would have occurred. But when she sends it, she is only doing so because she knew she had to. The event was shaped by her knowledge of the future, yet she only had that knowledge because the event had already happened. This paradox suggests that time may not work in a linear way. Instead of a simple progression from past to present to future, it might be shaped by feedback loops, where future events influence the past just as much as the past influences the future. In some science fiction stories, this paradox is explored through characters who receive messages, guidance, or knowledge from an unknown source. Later, they realize that they were the ones who provided the information in the first place. The loop continues indefinitely, with no true beginning or end. One possible resolution to this paradox is the idea that all events are fixed. This means that whatever happens in the future has already shaped the past in a way that cannot be undone. A time traveler may believe they are making a choice, but in reality, they are simply fulfilling what was always meant to happen. This idea eliminates contradictions, but also suggests that time travel does not allow for true change. Another possible resolution is that time is constantly shifting, and past events are in flux until they are finalized by future choices. This would mean that history is not fully determined until all possible choices have been made. In this view, reality would be shaped by decisions that extend across time rather than being locked into a single, unchanging timeline. The delayed choice paradox raises deep questions about how cause and effect function. It challenges the idea that time moves in only one direction. It suggests that the future and the past might be connected in ways that are difficult to understand. It also highlights the strange possibilities that arise when time travel is introduced into a system that normally follows logical cause and effect relationships. A traveler steps into a machine designed to send them back in time. They set the dial for a moment before a crucial event. Maybe it's something small, like a dropped cup that shattered on the floor. Or maybe it's something bigger, like the flick of a switch in a laboratory that starts a chain reaction. They arrive and act, changing what was supposed to happen. The cup doesn't drop. The switch doesn't flick. But now there's a problem. If they change the event, then the future they came from no longer exists in the same way. So how did they travel back in time at all? Quantum mechanics complicates time travel. It suggests that particles behave in unpredictable ways when observed, and that events may not always have fixed outcomes. In the classical view, an event happens, causes lead to effects, and time moves in one direction. But quantum mechanics allows for superposition, where a particle can be in multiple states at once until it is measured. It allows for entanglement, where one particle's state depends on another's even across vast distances. And it allows for the possibility that the past and future are linked in ways that defy common sense. A famous experiment highlights this strangeness. In the delayed choice quantum eraser experiment, a particle's behavior changes based on something that happens later. A photon passes through a barrier and splits into two possible paths. It moves toward a detector, which should reveal which path it took. But whether the path is revealed or hidden depends on a choice made after the photon has already traveled. This suggests that the future can affect the past, at least on a microscopic level. Now imagine applying this to time travel. A person goes back in time and changes an event. But what if the event exists in a quantum superposition, meaning it has multiple possible outcomes until observed? The traveler may expect a single version of history, but the moment they interfere, the past adjusts. Maybe they see two versions of an event overlap. Maybe they cause a paradox, where an event both does and does not happen at the same time. If quantum mechanics allows multiple possibilities to exist, time travel might create contradictions that can't be resolved. A scientist working on time travel might test this with a simple experiment. They send a small particle back in time, set to hit a detector. The detector is programmed to register the impact and erase the particle before it was sent. If the erasure works, then the particle was never sent. But if the particle was never sent, then how did it hit the detector? The contradiction doesn't make sense in classical physics, but in quantum mechanics, the answer might be different. The particle could enter a quantum state where it both exists and doesn't exist, much like Schrödinger's cat. It may form a closed loop where its existence depends on its own effect. Some scientists propose that quantum time travel avoids paradoxes by allowing histories to adjust. Instead of a paradox destroying logic, the past shifts to accommodate the traveler's actions. This idea, sometimes called the self-healing universe, suggests that changes made in the past always lead to the same future outcome. A traveler who tries to prevent an invention from being created might find that they only changed who invented it, not the invention itself. A traveler who tries to stop a war might find that the war happened for a different reason instead. Events adjust, keeping history intact. Another possibility is that quantum time travel creates new timelines. If reality follows the many worlds interpretation, then every quantum event splits into separate versions of the universe. A traveler who changes the past doesn't erase their own history, but jumps to a new timeline where events happen differently. In this view, time travel isn't a loop, but a branch, where new paths form whenever history is altered. The traveler may never return to their original timeline, meaning they can't undo their trip. A practical test of quantum time travel would require controlling tiny particles at a level far beyond current technology. Scientists have experimented with quantum teleportation, where information moves between entangled particles instantly, but this isn't the same as sending a physical object through time. For now, time travel remains a thought experiment. But if quantum mechanics allows the future to influence the past, then the paradoxes of time travel may not be as rigid as they seem. A person standing in a time machine might assume that changing the past would erase their future. But quantum mechanics suggests that the future isn't set in stone. It suggests that events can be linked in ways that seem impossible. A time traveler might step into the past and find that their actions don't create a paradox, but a shift. They might try to stop an event, only to realize that their interference was already part of history. They might change a small detail, only to watch the universe adjust around them. Time travel could be less about rewriting history and more about navigating a reality that is always in motion. Imagine a woman who undergoes an experiment in a hidden laboratory. Scientists want to test a theory about time displacement. They believe it is possible to move a person through time while their body remains unconscious. To eliminate outside influence, they sedate her before the procedure. The moment she loses consciousness, they activate the machine. She vanishes from the present and reappears in the past. The machine works, but there is a problem. When she wakes up, she does not remember the experiment. She does not know that she has been moved. She assumes she is waking up from an ordinary sleep, but nothing around her is the same. She stands in a room that belongs to someone else. The furniture is different. The air smells strange. She opens the door and walks outside, only to find a world that should not exist. If she had been awake for the transition, she might have understood what happened. But because she was unconscious, she has no memory of the moment of travel. She does not know if she belongs here, if she has gone into the past, or if she has entered a different timeline altogether. A person who time travels in their sleep might struggle to confirm what reality they have entered. If they have traveled backward, do they exist in the same form as before? Are they a duplicate of their past self, or have they replaced the version of themselves that should be here? If they have traveled forward, what happened to their original presence? If they skipped years or even decades, how does the world account for their absence? These are questions they cannot answer immediately because they have no way of knowing what process brought them here. A sleeping time traveler faces a greater challenge than one who is awake. Someone who chooses to travel through time can gather information, make plans, and control their movements. But if a person sleeps through the process, they wake up disoriented and unprepared. They do not know what caused their displacement. They do not know if they can return. The only way to find answers is to explore, ask questions, and hope that they can piece together the truth. Imagine a young boy who falls asleep in his bed one night and wakes up in the distant future. He is still the same age, but the world around him has changed. The house he knew no longer exists. The people who once cared for him are gone. He has no way to explain how he arrived here. He wanders the streets of a city that feels alien to him. The buildings are taller, the technology is unfamiliar, and the language has evolved into something he barely understands. He does not belong here, but there is no one to send him back. A person who time travels while unconscious must also question whether they have changed physically. If they traveled forward, have they aged? If they traveled backward, are they younger? A traveler who is awake might notice these changes immediately. They might see their hands wrinkle or smooth out. They might feel their body grow weaker or stronger. But a sleeping traveler has no way to observe these details until they wake up. Some theories suggest that a person who time travels without awareness might not be the same version of themselves when they wake up. If the body moves through time, but the mind remains unaware, does the consciousness adjust to the new reality? If someone wakes up in a timeline where they never existed, do they create a paradox? Do they replace another version of themselves, or do they become an anomaly in a world that was not expecting them? Consider the story of a man who sleeps through a time jump and wakes up to find his own grave. He does not know how long he has been gone. He does not understand why the world thinks he is dead. He looks for familiar faces, but the people he once knew have moved on. He cannot tell if he is a missing person or if history erased him completely. If he had been awake for the transition, he might have been able to adjust. But because he was unconscious, he has no memory of what happened. He must start from nothing, learning the rules of a time he was never meant to see. A sleeping time traveler must also consider whether they have traveled alone. If one person can time travel while unconscious, can others experience the same shift? If a group of people go to sleep and wake up in another time, how do they determine what caused it? Did they all move together, or did separate events bring them to the same place? If one person wakes up first, do they assume they are alone, only to find others later? If time travel occurs during sleep, does that mean it can happen naturally? Some believe that time travel requires technology, a machine, or an external force. But if a person moves through time without an explanation, is it possible that time itself is unstable? Does the body have an ability to slip through time without conscious effort? If one person can do it, can others? Does it happen more often than people realize, with some travelers waking up in new worlds while others remain unaware? A time traveler who wakes up in the wrong place must decide what to do next. They have no record of how they arrived. They have no guarantee that they can return. Their only choice is to adapt, to find answers, and to determine whether they are meant to be here at all. A man receives a letter one morning. The message inside warns him about a terrible fire that will break out at a nearby factory at exactly midnight. The letter does not say who sent it, but it includes detailed instructions on how to prevent the fire. At first, he dismisses it as a prank, but as the day goes on, he begins to worry. What if the warning is real? What if lives are at stake? He decides to follow the instructions, believing he can stop the fire before it starts. He arrives at the factory just before midnight. The building is dark and silent. He looks around but sees nothing unusual. Then, as he moves closer, he notices a suspicious figure carrying a gas can. Without thinking, he rushes toward the person, trying to stop them. In the struggle, the gas can spills. The fumes ignite, and within seconds, flames consume the building. In horror, he realizes what has happened. His actions did not prevent the fire, they caused it. Later, after the firefighters put out the blaze, he finds another letter waiting for him at home. It is the same letter he received that morning, written in his own handwriting. The predestination paradox is a problem that arises when a time traveler tries to change the past but ends up causing the very event they were trying to prevent. The key feature of this paradox is that the past remains fixed. Any attempt to alter it is part of a loop where the cause and effect feed into each other. The traveler has no real choice in the matter because their actions are already part of history. Consider another example. A man invents a time machine. He wants to use it to meet a famous scientist from 100 years ago. He travels back in time, but when he arrives, he finds that the scientist is not at home. Instead, there's a young student who appears eager to learn. Since he has come all this way, the man decides to talk to the student instead. They spend hours discussing ideas, and the student seems deeply inspired. Eventually, the man says goodbye and returns to his own time. When he checks the history books, he realizes that the student he spoke to was the scientist he had originally come to meet. His journey did not change history, it fulfilled it. This paradox shows up in many stories about time travel. A common version involves someone going back in time to stop a disaster. No matter what they do, their actions only ensure that the disaster occurs. If they try to stop an assassination, they might accidentally push the assassin's hand at the wrong moment. If they try to warn someone about an accident, their warning might be misunderstood, leading to the very accident they were trying to prevent. In every case, the time traveler's attempt to interfere only locks the event into place. A different take on the paradox involves objects that seem to appear from nowhere. Suppose a historian discovers a rare book with no known author. The book contains brilliant ideas that change the course of history. Years later, the historian builds a time machine and decides to bring the book back to the past, hoping to find out who wrote it. When he arrives, he realizes that no one has ever seen the book before. Not wanting to risk losing it, he publishes it himself. Over time, it becomes famous, eventually reaching his younger self. The book has no true origin. It exists because of a loop in time. Another version of the paradox involves personal identity. Imagine a woman who is fascinated by an old legend about a mysterious figure who saved her village centuries ago. As she grows up, she learns everything she can about the story. Then, one day, she gets access to a time machine. She decides to travel to the past to witness the event for herself. When she arrives, she finds the village in danger, just as the legend described. But there is no hero. In the moment, she takes action and saves the village. When she returns to her own time, she realizes the truth. She was the hero from the legend all along. These examples illustrate how time loops create closed systems. Events in the past cannot be changed because any attempt to do so will always lead to the same outcome. In a predestination paradox, the cause and effect reinforce each other. If a person receives a warning from their future self, they might act on it, believing they are making a free choice. But their actions only bring about the future that led them to send the warning in the first place. This paradox raises questions about free will. If someone tries to change the past and fails, does that mean their choices were meaningless? Or were they simply following a path that was always set? Some argue that the paradox suggests that time is fixed and unchangeable. Others believe that it only applies in specific cases where certain events must happen in order to maintain consistency. One way to think about the paradox is to imagine a movie that plays on an endless loop. The characters inside the movie might feel like they are making decisions, but every time the film starts over, they do the same things. If a time traveler is caught in a predestination paradox, their choices are already part of history. They might not realize it at first, but everything they do is necessary to bring about the events they already knew would happen. In some stories, people try to escape the loop by refusing to act. Suppose a man learns that he will one day be responsible for a tragic event. Hoping to avoid his fate, he locks himself in a room and refuses to go outside. But later, someone knocks on his door and asks for help. Unaware of who they are, he gives them advice that sets them on a path leading to the tragedy. By trying to avoid his destiny, he unknowingly ensures that it happens. Another variation involves self-fulfilling prophecies. If someone hears a prediction about their future, they might try to avoid it, but their actions only bring about the very outcome they feared. If a ruler is told that a young enemy will one day overthrow them, they might try to eliminate the threat. But in doing so, they might drive the enemy to fight back, turning them into the very person who will overthrow them. The paradox also appears in questions about knowledge. If a scientist from the future tells people in the past how to build a time machine, who actually invented it? The people in the past learned about it from the future, but the scientist in the future only knew about it because it already existed. The information has no true point of origin. It exists because of the loop. Some believe that the paradox suggests that time travel to the past is impossible. If any change leads to a closed loop, then there is no way to truly alter events. Others argue that time travel might work differently, allowing for multiple timelines or alternate realities. But in a strict predestination paradox, the future is already written, and time travelers only play their role in making sure it happens as it always did. A man finds an old book on advanced physics. The cover is worn, the pages yellowed. He studies it, amazed by its ideas. Over the years, he memorizes every word. He decides to rewrite the book by hand, copying it exactly as he found it. When he finishes, he takes the book back in time and leaves it in the past for someone else to discover. That person publishes the book, making it available to future generations. Eventually, the book reaches the man who originally found it. He studies it again, just as he did before. The cycle continues. The book has no true origin. No one ever wrote it. It simply exists, caught in a loop. This is the ontological paradox. It describes objects, knowledge, or people appearing in time without a clear point of creation. Something enters a time loop, existing indefinitely. It has no past, no moment when it was first made or discovered. It simply appears. A famous example is the story of a man who receives blueprints for a time machine. He follows the instructions and builds the machine. Once he finishes, he travels back in time and gives the blueprints to his younger self. His younger self then follows the same steps, creating the machine again and passing the plans back. The blueprints have no original author. They exist because they always have. Another example involves a musician. One day, she hears a beautiful melody played by an older musician. Inspired, she memorizes the tune and plays it years later. A young musician hears her play and, in time, performs it for someone else. The cycle repeats. The song has no composer. No one ever sat down and wrote it. It has always existed, moving through time in a loop. The ontological paradox challenges the idea that everything must have an origin. It suggests that some things might simply exist. This idea appears in many stories about time travel. In some cases, people try to break the loop. A scientist might ask, who actually wrote these equations? A traveler might wonder, where did this idea first come from? The answers never appear. The loop holds. This paradox often appears alongside the Bootstrap paradox. The two overlap. The Bootstrap paradox asks how something can be created from nothing. The ontological paradox asks how something can exist without a point of origin. In both cases, time travel creates a loop where cause and effect blur. A man steps into a time machine and travels to the future. He finds a famous painting, celebrated as a masterpiece. He carefully studies it, memorizing every brushstroke. When he returns to his own time, he recreates the painting exactly as he saw it. His version becomes the original. It is placed in a museum and eventually inspires the version he saw in the future. The painting has no original artist. It exists because it always has. In some versions of this paradox, people become trapped inside their own loops. A writer finds a manuscript that tells the story of his life. The book describes events he has not yet lived. He follows the book's instructions step by step, believing that his actions are his own choices. Eventually, he reaches the end. He realizes that he must now write the book, word for word, so that his younger self can one day find it. He does. The cycle repeats. The paradox forces questions about time, free will, and knowledge. If information exists in a loop, does it have an author? If a person only writes a book because they found a copy in the past, did they ever create the ideas inside? The loop removes the origin. It erases the starting point. The story of a scientist discovering an invention that has always existed follows the same pattern. A young engineer finds an old machine in a forgotten storage room. The design is brilliant, far ahead of its time. They reverse engineer it, creating blueprints and improving the design. Years later, they build a working model. The invention gains recognition. Decades pass, and the machine ends up in storage, waiting for someone to find it. The engineer never questions its true origin. The loop completes itself. Some versions of the paradox involve people rather than objects or knowledge. A man meets a mysterious stranger who helps him through a difficult time. Years later, he gains access to a time machine. He remembers the stranger's kindness and decides to travel back to help his younger self. He becomes the very person he once met. His actions ensure that the meeting happens exactly as he remembers. The loop continues. A common variation of the ontological paradox appears in fiction. A character receives an object from the future, like a watch or a weapon. They carry it with them for years, eventually traveling back in time and leaving it in the past. The object then makes its way through time until it reaches the character again. It has no creator. It simply exists. The paradox raises deeper questions about existence. If knowledge, objects, or people can appear in time without an origin, does this change how we understand reality? If an object has always existed in a loop, is it real? If a person is only born because they time traveled to the past and ensured their own birth, are they self-created? Some argue that the paradox breaks logic. Everything must come from somewhere. If something exists, it must have been created. But the ontological paradox suggests otherwise. It challenges the idea that events must follow a clear order. A man discovers a mysterious device. The machine allows him to send messages to the past. He tests it by sending himself a message about where to find the device. When he receives the message, he follows the instructions and retrieves the machine. He then repeats the process, ensuring the device always exists. The machine has no inventor. It appears in time as if it has always been there. Science fiction often explores the paradox through closed time loops. A scientist wakes up with an idea for a revolutionary formula. She writes it down, unaware that she will one day send it back in time. Years later, she refines the formula and sends it to her past self. She remembers receiving it, but never questions its true source. The paradox creates scenarios where knowledge exists without discovery. A person reads a history book that describes an event in detail. Later, they time travel to that period and become the person who causes the event. They ensure that history unfolds as written. The book exists because it always has. This concept raises questions about free will. If a person exists only because they time traveled to the past and ensured their own existence, did they ever have a choice? If a musician plays a song that was never written, is it their creation? If an invention appears from nowhere, does it belong to anyone? Time travel stories use the ontological paradox to explore cause and effect. The loop prevents change. It ensures that events unfold as they always have. In some stories, characters try to break free. They question their reality, searching for an answer that does not exist. The loop holds. A scientist builds a time machine after studying designs found in an old notebook. Once the machine is complete, they travel back and leave the notebook for their younger self to find. The younger self follows the instructions and builds the machine again. The cycle continues. The machine has no true creator. It exists because it always has. This paradox suggests that some things might never have an origin. It challenges the way people think about time. It raises questions that have no clear answers. The loop continues unchanged. A man discovers a book on advanced physics. He studies it, memorizes its contents, and later in life, he travels back in time with the book. He hands it to a young scientist in the past, who then publishes it under their name. The book becomes famous, inspiring generations of scientists. Eventually, the book is found by the same man when he is young, beginning the cycle again. At no point in this sequence was the book ever written by an original author. It simply exists, passed from one point in time to another without an origin. The bootstrap paradox creates a loop where an object, idea, or piece of information has no clear point of creation. It exists because it was brought from the future to the past and then carried forward again. This paradox raises the question of where things truly originate and whether time travel allows something to exist without a creator. A common example used to illustrate this paradox involves William Shakespeare. Imagine a time traveler who loves Shakespeare's works and memorizes his most famous plays. Wanting to meet the famous playwright, they travel back to the 16th century. When they arrive, they discover that Shakespeare is struggling to write and hasn't yet produced anything. Worried that history may change, they write down the plays from memory and hand them to Shakespeare, who then publishes them under his name. This creates a loop where Shakespeare's works exist because they were given to him by someone who had already read them in the future. But if Shakespeare never wrote them in the first place, where did they come from? Another way to think about the bootstrap paradox is through technology. Suppose a scientist in the future builds a time machine. Before they can reveal their invention, someone from the future visits them and hands them blueprints for the exact same machine. The scientist follows the blueprints and builds the machine. Years later, when they are older, they travel back in time and hand the blueprints to their younger self, ensuring the cycle continues. At no point was the design originally created. It has always existed within the loop, appearing to have no origin. This paradox challenges the way people think about causality. Normally, an event has a cause, and that cause has its own cause, forming a logical chain that moves forward in time. The bootstrap paradox disrupts this order by creating a loop where something exists without a first cause. It is similar to the question of the chicken and the egg. If a chicken lays an egg, which hatches into another chicken, the cycle continues indefinitely. But what if someone found an egg, went back in time, and gave it to the first chicken? Then the egg would exist without a clear point of origin. The paradox is named after the idea of pulling oneself up by one's bootstraps, an impossible task. In literature and media, the bootstrap paradox appears often in time travel stories. In the television series Doctor Who, the protagonist describes the paradox with a simple example. A time traveler loves Beethoven's music and wants to meet him. They go back in time to the period when Beethoven was alive, but they discover that he doesn't exist. To ensure that history remains unchanged, they copy down Beethoven's music and publish it under his name. Over time, this music inspires the same traveler in the future, who eventually goes back to repeat the process. In this case, Beethoven's music exists only because the traveler brought it back, but it was never originally composed. The paradox becomes even more confusing when applied to knowledge. Suppose a historian in the future finds a detailed record of an ancient civilization that no one had ever seen before. The historian, eager to learn more, travels back in time and shares this knowledge with the people of that civilization, who then document their history based on what they have been told. Thousands of years later, the same historian discovers these records and learns from them, completing the loop. The history of the civilization exists, but it has no real beginning. One of the strangest things about the Bootstrap paradox is that it does not seem to break the laws of physics directly. In some interpretations of time travel, the paradox is simply a self-consistent loop where events happen in a closed cycle. Nothing is changed and no contradictions appear. However, it does create a logical puzzle, since everything within the loop lacks a point of origin. If time travel were possible, the Bootstrap paradox would raise questions about where ideas, inventions, and works of art truly come from. If a scientist in the future builds a groundbreaking invention and then travels back in time to give it to an earlier scientist, who then claims credit for it, who actually invented it. If a poet memorizes famous works from the future and gives them to a writer in the past, who then publishes them, where did the poetry originate? The paradox suggests that information and objects might be able to exist without creation. If a person builds a time machine and then gives themselves the plans for it from the future, they never had to figure out how to build it in the first place. The design simply exists within a loop. This idea challenges the traditional view of cause and effect, making time travel a difficult concept to resolve logically. In science fiction, the Bootstrap paradox often appears as a storytelling device. In some cases, it is used to create mystery, where characters must figure out how something exists if no one ever originally created it. Other times, it serves as a way to explore the consequences of time travel, showing how events might repeat in ways that defy normal logic. A well-known example from film is in the Terminator series. In the story, a company called Cyberdyne Systems creates a powerful artificial intelligence called Skynet. However, the technology that allows them to build it comes from a damaged robot sent from the future. The robot is destroyed, but the pieces are used to reverse engineer the advanced technology. This leads to the development of Skynet, which eventually creates the robot that is sent back in time. This loop ensures that the technology exists, but it was never actually invented in the first place. It exists only because it was brought from the future. The Bootstrap paradox highlights the strange nature of time loops and the way they disrupt normal cause and effect. If time travel is possible, it raises the possibility that knowledge, inventions, and even entire histories might exist without an origin. This creates a puzzle that remains unsolved, leaving open the question of whether time travel can truly function in a way that makes logical sense. A person steps into a time machine and travels back 100 years. They arrive in the early 1900s, blending into society. Over time, they meet someone, fall in love, and have a child. That child grows up, has a family, and through the generations, their own lineage continues. Eventually, one of their descendants is born in the present day, the same person who originally stepped into the time machine. They have traveled back in time and unknowingly become their own ancestor. There is no clear beginning or end to their existence, just an infinite loop of events where they cause themselves to be born. This paradox creates a problem with causality. Normally, every person comes from a set of parents who come from their own parents, stretching back in a continuous chain. Each person exists because of biological reproduction that follows a clear timeline. But in this case, the origin point disappears. The traveler was born because they went back in time and caused their own birth. This means their existence is self-created. There is no original ancestor, no first person to start the cycle. The entire chain of events loops back on itself, which defies how cause and effect usually work. This paradox is sometimes called the ontological paradox, but the self-creation paradox is a more specific version. It deals with a person instead of an object or idea. It's a problem because it challenges the way time and reality work. Normally, things exist because something caused them to exist. A book is written by an author, a painting is created by an artist, a machine is built by an engineer. But in the case of the self-creation paradox, there is no true creator. The person who exists was never originally born in a normal way. They were only born because they traveled back and caused it to happen. Think of another scenario. A baby is left on the doorstep of an orphanage in the year 1900. The people running the orphanage take the baby in, but they don't know where the child came from. The baby grows up, eventually discovers time travel, and decides to go back in time to investigate their origins. They travel back to the year 1900 and see a familiar scene, a baby being left on the doorstep of an orphanage. They realize they are the one who left the baby there. In other words, they place themselves in history. There was never a moment when the baby was originally born. It was just placed into time by the same person it would later grow into. This idea also appears in fiction. Robert Heinlein's short story All You Zombies tells the story of a person who, through a series of time travel events, ends up being both their own mother and father. Every step in the cycle is created by another step in the same cycle. There is no beginning. Each action just loops back to create itself. This highlights the central issue with self-creation. Where did it all begin? If someone exists only because they traveled back in time, then what was their true starting point? Science fiction often explores this paradox because it presents a deep problem for how we understand time. If someone can be their own ancestor, then the normal rules of history no longer apply. It means a person can exist without needing a first cause. But that contradicts how everything else in reality works. If something exists, there must be a reason for it. A planet forms because of gravity pulling material together. A person is born because of biological reproduction. A building stands because it was designed and constructed. But in a self-creation loop, there is no original cause. The person just is. They exist without ever truly being created. One way to look at this paradox is through the idea of a closed time loop. In normal time, events happen in a straight line. One thing causes another, which causes another, and so on. But a closed time loop is different. It doesn't go in a straight line. Instead, it folds back on itself, so that events keep repeating with no clear beginning. A self-created person exists in this loop. They are born because they go back in time, and they go back in time because they are born. There is no starting point. It's just a cycle that keeps itself going. Some people argue that this type of paradox could never happen. They believe the laws of nature would prevent it. Others suggest that time travel might work in a way that allows for loops like this, but we don't fully understand how. If time travel ever becomes possible, we may have to rethink how causality works. Could the universe allow a person to create themselves? Or would some unknown rule prevent it? The self-creation paradox also raises questions about identity. If someone goes back and causes their own birth, who are they? Are they a normal human, or are they something different, something outside of the usual rules of time? If there is no original version of them, are they real in the same way that other people are? Most people have a clear origin. They are born at a specific time to specific parents. Their past is fixed and known, but a self-created person has no fixed origin. Their past is a loop, not a straight line. This challenges our basic understanding of what it means to be a person. It also creates issues for free will. If a person exists only because they went back in time, do they have any choice in the matter? Could they decide not to go back, or is the loop unbreakable? If they choose not to travel back, then they were never born, which means they never had the choice in the first place. This raises a troubling question. Is their life truly theirs, or is it locked into a predetermined path? If their past is already written, does that mean their future is also fixed? This idea connects to other time travel paradoxes, like the predestination paradox, where attempts to change the past always end up preserving it. Another problem with the self-creation paradox is the issue of genetic material. In normal reproduction, two parents contribute DNA to create a new person. But in a self-creation loop, where does the genetic material come from? If the traveler is their own ancestor, then their DNA must come from themselves. But that creates an endless cycle with no original source. In real biology, DNA mutates over time, and new traits appear through mixing genetic material from different people. A person who is their own ancestor would have no genetic diversity. In reality, this would likely cause problems over generations, as mutations and errors accumulate without new genetic material being introduced. The paradox becomes even more complex when considering changes to history. If someone is their own ancestor, then history must remain stable to ensure they exist. But what happens if an outside force interferes? What if someone else time travels and disrupts the cycle? Would that erase them from existence? If so, then their entire timeline is fragile, dependent on every event happening exactly as before. But if their timeline is flexible, then that suggests they could change their own history, raising even more questions about causality. The self-creation paradox highlights one of the biggest problems with time travel. It breaks the normal cause and effect relationship that governs the universe. In our everyday experience, things exist because something caused them to exist. The self-creation paradox removes that cause, leaving only an endless loop with no beginning. If time travel ever becomes a reality, we may have to face the possibility that such paradoxes could exist. But for now, they remain thought experiments, questions about what might happen if time were not as simple as we think. A man discovers a way to travel back in time. He has always been fascinated by history, and one event in particular stands out in his mind: the assassination of Archduke Franz Ferdinand in 1914. He believes that if he can prevent the assassination, he can stop World War I from happening. With this goal in mind, he sets the controls on his machine and steps back in time. When he arrives, he finds himself in Sarajevo on the morning of June 28, 1914. He knows exactly what is about to happen. The assassin, Gavrilo Princip, will fire his gun and kill the Archduke. If the time traveler can intervene, history could change. He positions himself along the route of the motorcade, determined to stop Princip before he can pull the trigger. But no matter what he does, something prevents him from succeeding. He tries to push the assassin away, but someone in the crowd bumps into him at the last second. He attempts to warn the Archduke's guards, but they don't believe him. He even considers knocking the gun out of Princip's hand, but an unexpected obstacle appears. The shot is fired. The event happens exactly as history recorded it. No matter how many times he tries, he cannot stop the assassination. It's as if the past resists change. Every action he takes somehow becomes part of history instead of altering it. He begins to understand that he was always there. The history books didn't mention him, but he was in the crowd all along. His efforts to prevent the assassination were part of the event itself. This is the consistency paradox. It suggests that time travel to the past cannot change history. Any attempt to alter events will either fail or become part of the existing timeline. The past is fixed, and nothing a time traveler does will contradict what has already happened. Some scientists and philosophers argue that if time travel were possible, the universe would protect its own timeline. The laws of physics or probability would ensure that events unfold the way they always have. This idea removes the problem of paradoxes, like the grandfather paradox, where a person prevents their own existence by changing the past. If the past is immune to change, then these contradictions never occur. A woman tests this idea by traveling to the 1960s. She wants to warn a scientist about an upcoming disaster, hoping to change the course of history. She manages to find the scientist and tells him what she knows. But instead of acting on her warning, he dismisses her as a conspiracy theorist. She tries to leave behind evidence, but it gets lost or ignored. Frustrated, she returns to her own time, only to find that nothing has changed. The disaster still happened. Looking deeper, she realizes that she was always part of history. She was recorded in documents as an unknown woman who made strange predictions. Her warning didn't change anything. It was already part of the past. Her trip was not an alteration of history, but rather a fulfillment of it. The consistency paradox suggests that no matter what a time traveler does, their actions have already been accounted for. They cannot create a contradiction because the timeline has already included them. If a person travels to the past and tries to change something, they were already there in the original version of events. Their attempts, failures, and even their successes were always part of history. Imagine a young man who finds an old book filled with detailed notes on physics. The book is written in his own handwriting, but he doesn't remember ever writing it. The notes help him develop new theories and eventually lead him to invent time travel. He decides to go back and leave the book for his younger self, ensuring that he will discover it and follow the same path. The book has no clear origin. It exists in an endless loop, passed from one version of the man to another, never truly being created. This is another way the consistency paradox appears. Objects, ideas, and even people can exist in time loops, but they cannot be changed or removed, because they were always part of history. A man tries to destroy an important historical document by traveling to the past and burning it before anyone can read it. But when he returns to his own time, he finds that the document still exists. He checks the historical records and discovers something strange. The original document was never found in perfect condition. It was always partially burned. His attempt to destroy it was not an alteration, but rather the reason for its damaged state. He realizes that he was responsible for the very thing he was trying to prevent. A woman wants to witness the signing of the Declaration of Independence. She travels back to 1776 and manages to blend into the crowd. She doesn't interfere, knowing that history must play out as recorded. But while she watches, she accidentally drops a modern coin from her pocket. It rolls across the floor, unnoticed by most. Centuries later, archaeologists discover an out-of-place coin from the future, buried beneath the site of the signing. The woman's trip did not change history. It simply revealed that she was always part of it. Some argue that the consistency paradox means free will does not exist in a timeline where time travel is possible. If a person cannot change the past, then their choices were predetermined. They may feel like they are making decisions, but those decisions always lead to the same outcome. A man who travels to the past to save a loved one may find that every action he takes brings about the very event he was trying to prevent. He is not altering the past. He is ensuring that it happens as recorded. This paradox appears in myths and stories throughout history. The tale of Oedipus is one example. A prophecy warns Oedipus's father that his son will one day kill him. To prevent this, he abandons the child, but this very act leads to the child being raised by another family, unaware of his origins. Later, Oedipus unknowingly fulfills the prophecy by killing his father in a chance encounter. The attempt to prevent the future causes it to happen. This is similar to how time travelers who try to change history often become the reason it unfolds as it does. A scientist builds a machine that lets him send messages to the past. He sends a warning about a coming disaster. When he checks the records, he sees that someone in history did, in fact, receive an anonymous message predicting the event. The scientist realizes that he was always the sender. His message did not change history. It was always part of it. A group of historians tests time travel by sending someone to the past to learn about a lost civilization. When the traveler arrives, they try to blend in, but the locals mistake them for a god, and they become part of the civilization's mythology. Centuries later, scholars study ancient texts and find descriptions of a mysterious visitor who matches the traveler's appearance. They realize that the time traveler was always part of history. The consistency paradox suggests that time travel cannot create contradictions. The past is already set, and any attempt to change it only confirms what was always meant to happen. A person may feel like they are making choices, but those choices have already been accounted for in history. Whether through direct action or unintended consequences, they fulfill their role in the timeline exactly as it was recorded. A time traveler steps into a machine, sets a date in the past, and disappears. They arrive decades earlier in the same location. The moment they appear, an extra mass has entered the system. If energy cannot be created or destroyed, where does the energy for their body and machine come from? If they return to the future, does the energy leave with them, or does it stay? If they travel forward in time, does the past lose energy when they disappear? These questions highlight a fundamental problem with time travel and the law of conservation of energy. Physics states that in a closed system, the total amount of energy remains constant. It can change form, like when chemical energy in food becomes kinetic energy in movement, but it does not appear or vanish. The universe is the ultimate closed system, so energy should always remain the same. If time travel allows mass and energy to shift between different points in time, it suggests a system where energy can be added or removed from different eras, violating this law. Imagine a person travels from 2025 to 1925. The moment they arrive, the universe in 1925 has more energy than it should. Their body, the time machine, even the air displaced when they materialize, all of it adds mass and energy. If they brought a smartphone, it contains batteries charged with energy that did not exist in 1925. They could light a bulb using stored electricity that was supposed to be in the future. If they never return, this energy stays in the past. Over billions of years, even small changes could add up, shifting the balance of the universe. Now consider the opposite. If a person leaves 2025 and appears in 1925, then for an instant in 2025, the total energy of the universe drops. If they disappear permanently, the universe has permanently lost mass and energy. This breaks a fundamental rule of physics. The problem becomes worse if multiple time travelers move across time. If people and objects are constantly moving to the past, the present could lose energy at a rate that makes it unstable. One possible way around this is the idea that energy is not lost but displaced. When the traveler moves to 1925, perhaps an equivalent amount of energy vanishes from 2025. Maybe the universe balances itself by converting energy into another form, or maybe time itself is structured to prevent an imbalance. This would mean time travel is possible, but only if the total energy remains constant across time. Some theories suggest the universe might correct itself through something like time elasticity. If too much energy is added to one point, small adjustments occur elsewhere to maintain balance. The universe could redistribute energy over time to prevent a buildup or loss. This would mean travelers might unknowingly trigger compensations, like heat dissipating slightly faster in another part of space or matter becoming slightly less dense in another region. Another possibility is that time travel creates a new timeline rather than altering the same one. If each trip forms a separate reality, the law of conservation of energy applies only within each version of time. The traveler does not disrupt the energy of their original timeline, but instead enters one where their presence has always been accounted for. In this model, energy is conserved within each separate timeline, avoiding contradictions. A different approach is to assume that time travel can only happen under strict physical limits. Maybe only information can be sent back in time, not physical objects. If someone could send knowledge rather than their physical form, then the paradox would not occur. A message sent to the past does not add new mass to an earlier time, avoiding an energy surplus. If this were the case, time travel could be possible, but only in a way that does not allow people or objects to move between different points. Another consideration is how the universe might respond to an increase in energy. If time travelers appear in the past, bringing extra mass and energy, could the universe adapt? Maybe the excess energy spreads out or disperses in a way that does not disrupt the overall balance. If this were true, time travel might involve unpredictable side effects. A sudden shift in energy might trigger natural events, such as slight temperature shifts, increased cosmic radiation, or tiny changes in planetary motion. These effects would be small, but could add up over time. Some scientists argue that conservation of energy applies only in a single timeline, not across time travel events. If a time traveler leaves the present and enters the past, the energy might still exist in the same universe, just at a different moment. This interpretation suggests that while it appears energy is added or lost at specific moments, the overall system remains balanced when viewed across the entire timeline. One approach to solving this paradox involves considering quantum mechanics. Some theories suggest that energy may not be strictly conserved in short time intervals, but only in the long term. If this is true, Temporary fluctuations could allow brief violations of conservation laws, meaning time travel might not be impossible under certain conditions. However, these fluctuations happen on scales far smaller than a person or machine, making them unlikely solutions for practical time travel. Another possibility is that time travel is naturally restricted to prevent these problems. Some theories suggest that if a person attempts to travel back in time in a way that breaks energy conservation, the event never happens. The universe might prevent paradoxes by making certain time travel events impossible. If someone builds a machine that should allow travel to the past, physical laws might intervene, breaking the machine, stopping it from working, or preventing the necessary conditions. Some speculative ideas suggest that if time travel were possible, the entire universe might adjust itself in ways we do not understand. If mass and energy are added at one moment, the universe might redistribute them through unknown mechanisms. These ideas remain highly theoretical, as there is no evidence that such corrections occur. If time travel works without violating conservation laws, then something must account for the extra energy. The missing piece of the puzzle could involve unknown physics, interactions between time and space, or hidden variables. Until a working time machine is built, the full impact of time travel on energy conservation remains uncertain. A man steps into a time machine with a simple goal. He wants to change history, but only in the smallest way possible. Instead of stopping a major event or preventing a catastrophe, he wants to make a tiny adjustment, a single moment, an action so minor that it should have no noticeable effect. He selects a day in the past and sets his machine to take him there. When he arrives, he finds himself in a familiar setting. He recognizes the people, the buildings, and the landscape. Everything is exactly as he studied before making the trip. He walks to a street corner, picks up a small pebble, and moves it a few inches to the left. Then, satisfied that he has successfully altered the past, he steps back into his machine and returns to his original time. When he arrives back in the present, nothing seems different. The world appears unchanged. He checks the news, his family, and his surroundings. He cannot find a single thing out of place. Did his action matter at all? If he moved 1,000,000 pebbles instead of one, would he have noticed a change? How much of the past must be altered before the future is meaningfully different? Zeno's time travel paradox raises this question by considering the nature of infinite small changes. The paradox is inspired by the ideas of Zeno, an ancient Greek philosopher known for his paradoxes of motion. One of his most famous thought experiments asks whether someone can ever truly reach a destination if they must always cross half the remaining distance. Each step forward gets smaller and smaller, but the person never actually arrives. Applied to time travel, this idea creates an unsettling problem. If a time traveler makes an infinite number of small changes to the past, do those changes ever truly add up to something significant? Or does the nature of time itself prevent them from having any real effect? To explore this paradox, imagine another traveler who wants to test the limits of small changes. Instead of moving a single pebble, he decides to pluck a single blade of grass from a field. He does this, then returns to the present. Again, nothing seems different. Encouraged by this, he makes another trip and plucks another blade of grass. He repeats this experiment thousands of times. At what point does history begin to change? If he removes one more blade, does that become the critical moment that shifts the course of time? Or does the past resist small changes, absorbing them without altering the future? The problem becomes even more complicated when considering the butterfly effect, the idea that even tiny actions can lead to significant consequences over time. If a single butterfly flapping its wings can theoretically contribute to a storm on the other side of the world, shouldn't moving a single pebble have a similar effect? If that's true, why doesn't the time traveler see any changes? The paradox suggests that either small changes don't matter at all, or that time has a way of self-correcting to prevent them from having an impact. Another way to examine this paradox is through a more extreme version of the experiment. Instead of removing a blade of grass, the traveler decides to make an even smaller change. He chooses a single grain of sand on a beach and moves it 1 millimeter. Surely such a small action could not possibly change history. But what if he moves another grain, and another? over an infinite number of trips, he eventually shifts the entire beach. Has he changed history yet? If not, why? If so, when did the shift occur? Now consider an alternate version of the problem. Instead of changing the past, the traveler decides to create the future through small, incremental steps. He places a single grain of sand in an empty desert. Then he adds another, then another. Eventually, he deposits billions of grains and forms an island. At some point, the island becomes large enough for people to live on. At some point, it gains significance. But when does this transition happen? If the addition of a single grain does not make an island, how can billions of single grains ever form one? This is where the paradox forces a difficult question. If time travel allows for an infinite number of small changes, is there a threshold at which those changes become meaningful? Or does time smooth out all alterations, preventing any real divergence from history? If the latter is true, then the past may be more resistant to change than people assume. One explanation for this paradox is that time itself has a form of inertia. Just as a moving object resists changes in motion, time may resist changes in its flow. If this is true, then small changes in the past are absorbed by the timeline without altering the future in a significant way. This would mean that no matter how many pebbles are moved, how many blades of grass are plucked, or how many grains of sand are shifted, history remains intact. Only large-scale events, ones that dramatically impact human decisions or natural phenomena, might be capable of causing real change. Another possibility is that small changes do matter, but their effects are hidden or delayed. A traveler may not see an immediate difference, but over time, the accumulation of small actions may build into something unrecognizable. Perhaps moving a single pebble prevents an ant from crossing a path, which changes the course of its life, which in turn affects a predator that relies on it for food, which in turn influences an entire ecosystem. The effects may take decades or centuries to manifest, but eventually, history could be completely different. But if this is true, then how can a time traveler ever predict the consequences of their actions? If even the smallest change has an eventual impact, then every action becomes a potential cause of massive disruption. In this view, time travel becomes a game of chance, where any trip to the past might unknowingly create a future that the traveler could never anticipate. Some theories attempt to resolve this paradox by introducing the idea of multiple timelines. Instead of changing a single history, each action creates a new branch in time, forming an alternate reality. In this scenario, the traveler does not actually alter their own past, but instead shifts into a parallel timeline where events play out differently. The original timeline remains untouched, and all small changes simply create an expanding web of possible worlds. But this raises another issue. If every small action results in a new timeline, then an infinite number of universes must exist to accommodate every possible variation. If a traveler shifts a grain of sand and creates a new reality, what happens when they shift another grain? Does that create yet another branch? If so, the number of possible futures becomes overwhelmingly large, stretching beyond human comprehension. This paradox ultimately forces a reconsideration of how time travel might function. If history is resistant to change, then travelers may never be able to alter the past in a meaningful way. If every small action has an impact, then time travel may be too unpredictable to control. Either way, Zeno's time travel paradox challenges the idea that time can be easily manipulated. A person builds a time machine and decides to test it by traveling back to the early 1900s. They set the machine to take them to a time before their grandfather met their grandmother. They arrive in a small town and find themselves in a world very different from their own. The streets are filled with early automobiles, people wear old-fashioned clothes, and electricity is not yet widespread. The time traveler knows they must be careful. Any action they take could change the course of history. While exploring, they see a young man who looks familiar. After watching him for a while, they realize this man is their grandfather. At this moment, the time traveler faces a question. What happens if they interfere with his life? If they somehow prevent him from meeting their grandmother, their parent will never be born. Without their parent, they will never be born either. If they are never born, how could they have traveled back in time to stop their grandfather from meeting their grandmother? This paradox challenges the basic idea of cause and effect. Normally, every event has a cause that comes before it. The past influences the present, and the present influences the future. But time travel turns this logic upside down. If a person can travel to the past and change events, they can remove the very conditions that allowed them to exist. This creates a contradiction. To understand the problem, imagine a simple version of the paradox. A man travels back in time with the goal of preventing his grandfather from surviving a particular event. He succeeds. Now his grandfather never has children, which means the time traveler is never born. But if the time traveler is never born, how did he go back in time in the first place? There is no logical way for both of these statements to be true at the same time. Some people try to solve the paradox by suggesting that time corrects itself. According to this idea, something would prevent the time traveler from changing history in a way that causes a contradiction. Perhaps they would accidentally fail in their attempt, or an unexpected event would block them at the last moment. No matter what they do, their grandfather would still meet their grandmother, and history would stay the same. This idea suggests that the past is fixed and cannot be changed, no matter how hard someone tries. Others propose an alternative explanation. Instead of history correcting itself, time travel could create a new timeline. When the time traveler prevents their grandfather from meeting their grandmother, they do not erase their own existence. Instead, they create an alternate version of history where they were never born. But in their original timeline, they were still born and traveled back in time. This idea suggests that time travel works by creating parallel universes rather than changing the past. Some scientists argue that time travel to the past may be impossible for exactly this reason. If a person could change the past, they could create paradoxes that defy logic. This would suggest that time travel can never happen, at least in a way that allows changes to history. Others argue that time travel might be possible, but that the laws of physics prevent paradoxes. They suggest that events would always play out in a way that avoids contradictions. Science fiction often explores these ideas. Many stories use the grandfather paradox as a central plot point. In some stories, a time traveler accidentally changes the past and erases their own existence. In others, time corrects itself in strange ways. A person might try to prevent an event, only to realize later that their actions caused it to happen in the first place. These stories highlight the strange consequences of time travel and make people think about the nature of time and reality. Another version of the paradox involves smaller changes to the past. Instead of preventing their grandfather's birth, the time traveler makes a small change that affects their own life. Perhaps they convince their grandfather to move to another country. This means he never meets their grandmother, and the time traveler is never born. But if they were never born, they could not have traveled back in time to convince him to move. The contradiction remains. Some people suggest that free will would play a role in time travel. If a person went back in time, they might have the ability to change small details but not major events. Perhaps they could talk to people or move objects, but something would always prevent them from making changes that cause paradoxes. This idea is similar to history correcting itself, but suggests that certain events are fixed points in time. The paradox also raises questions about identity. If a person goes back in time and changes their family history, are they still the same person? If their grandparents never met, their parents never existed in the same way. This means their DNA would be different. Even if someone else was born in their place, that person would not be them. This means the time traveler is not just erasing their existence, but replacing themselves with a completely different version of reality. This problem applies to any change in the past. If a person goes back in time and makes a small adjustment, they risk altering events in ways they cannot predict. A single conversation could change someone's decisions, leading to a different chain of events. Over time, these small differences add up. The farther back a person travels, the greater the risk of changing history in unintended ways. There are also ethical questions. If time travel were possible, should people be allowed to change the past? If someone could prevent a major historical tragedy, should they do it? What if preventing that tragedy caused worse events in the future? These questions make the paradox even more complicated. The paradox does not only apply to people, it can involve objects and information as well. Imagine a scientist travels back in time and gives a famous physicist the equations for a groundbreaking theory. The physicist publishes the theory, and the equations become widely known. Later, the scientist learns about the equations and decides to take them back in time to share with the physicist. But if the scientist only learned about the equations because they already existed, where did they originally come from? This is another version of the paradox, where something exists without an original cause. The paradox also raises questions about determinism. If time travel is possible but paradoxes must be avoided, does this mean that all events are predetermined? If a person tries to change the past and always fails, does this mean they never had free will in the first place? Some theories suggest that time is a fixed loop where all events are already set in place. If a person time travels, they were always meant to do so, and their actions were already part of history. There is no clear answer to the paradox. Scientists and philosophers continue to debate its implications. Some believe that time travel is simply impossible, while others think that the universe would find a way to prevent contradictions. The paradox remains one of the most famous thought experiments in discussions about time and reality. You step into a time machine. The controls glow softly, and a few button presses later, you are on your way to the past. You have one goal in mind: to stop yourself from ever existing. Maybe life has become unbearable. Maybe you believe the universe would be better off without you. Whatever the reason, you set your destination to a point in time before you were born, locate your parents, and prevent them from ever meeting. Or perhaps you go further back and eliminate an ancestor, ensuring that you never come into existence. The problem is, if you never exist, how did you travel back in time in the first place? This is the retroactive suicide paradox. Time travel creates strange loops where actions in the past should affect the future. But in this case, the contradiction is immediate. If you succeed in erasing yourself, then you were never born, never grew up, never built or used a time machine, and never traveled back to the past. Yet there you are, in a time before your birth, interfering with events. This paradox forces a contradiction between cause and effect. Your actions in the past should have erased the version of you that made those actions possible. But if that version of you never existed, then who carried out those actions? Consider another version of the paradox. Suppose you travel back in time and directly confront your younger self. The person standing in front of you has no idea that they will one day grow up to become you. You take a weapon, pull the trigger, and watch as your younger self collapses. The instant they die, the logical outcome should be that you, the older version, cease to exist. But if you vanish, then there was no one to go back in time and cause the event. And if that event never happened, then your younger self survives and continues on to become you, allowing you to travel back in time once again. The cycle repeats with no resolution. The paradox emerges from the conflict between logic and time travel. In a normal cause and effect sequence, an event happens and leads to a consequence. A person is born, grows up, makes decisions, and experiences outcomes. In time travel scenarios, these sequences are broken. The effect, the time traveler erasing themselves, eliminates the cause, the time traveler existing to take that action. The contradiction leaves no clear answer to what actually happens. Some theories attempt to explain how this paradox might resolve. One possibility is that the universe simply does not allow these kinds of contradictions. This is sometimes called the Novikov self-consistency principle, which suggests that time travel is possible but paradoxical changes are not. If a time traveler tries to create a paradox, some force or coincidence will always prevent them from succeeding. The gun jams. The time machine malfunctions. They lose their resolve at the last second. No matter what they do, events conspire to make sure they never actually erase themselves from existence. Another explanation is the branching timeline theory. Instead of altering the past in a way that affects their own existence, the time traveler creates an alternate reality. In this version, they go back, cause their own death, and erase the version of themselves in that timeline. But since they originally came from a separate timeline, their existence is not immediately undone. The original timeline, where they existed and made the trip, still exists separately. The problem with this idea is that it does not truly resolve the paradox. It just shifts the contradiction into a different reality. The time traveler still originates from a past that should not have happened. A third perspective is that time travel does not rewrite history, but instead overwrites the present. This would mean that the moment a time traveler erases themselves, they immediately cease to exist, and the timeline resets to a version where they never traveled back. The moment of erasure is the final event, locking the universe into a state where they were never born and never traveled through time. But this creates a different problem. If the reset removes the time traveler, then the trip to the past never happened, and there was no event to cause the erasure. This loops back into the same contradiction. Some fictional stories have played with this paradox in different ways. In certain interpretations, time travelers who erase themselves simply fade out of existence as though they were never there. They experience their own erasure as a slow process, watching as their presence in the world is undone. Others depict the paradox as creating a logical breakdown, a situation so impossible that the universe reacts violently. Some stories show time collapsing in on itself, breaking down in ways that cannot be fully understood. The universe, unable to handle the contradiction, either destroys itself or resets everything. Even if one assumes that time travel is theoretically possible, this paradox suggests that there must be rules preventing contradictions. If unrestricted, time travelers could erase themselves, leading to a scenario where they both do and do not exist. Logic cannot allow both conditions to be true at the same time. Something must give way. Either paradoxes prevent themselves from forming, or time travel is not possible in a way that allows these contradictions. The retroactive suicide paradox is a strong argument against unrestricted time travel. It highlights the issue of self-causation and the fragility of altering the past. If changing history removes the reason for traveling in time, then the change itself should not have happened. But if the change never happened, then history remains the same, and the traveler still exists, meaning they could go back and change things. The cycle loops endlessly without a stable resolution. Even without time machines, similar ideas come up in everyday logic. Think of an event that depends on itself to occur. If you go back in time to give yourself advice that makes your life better, did the advice ever truly originate? If you stop a disaster from happening but remove the reason you intervened, does the disaster still need to be prevented? These thought experiments reveal the core problem of retroactive changes. No clear solution exists to this paradox. If time travel were ever discovered, some form of constraint would likely prevent people from making changes that eliminate their own existence. Whether that happens through natural law, multiple realities, or hidden mechanisms in time itself is unknown. What is clear is that any scenario where a person removes themselves from existence leads to a contradiction. Cause and effect cannot function if the effect erases its own cause. The paradox forces the question of whether time is truly flexible or if it follows a strict set of rules. If past events can be rewritten freely, then logic breaks down when those changes prevent the very actions that created them. If time is rigid, then attempts to alter it must fail in some way that preserves consistency. The debate continues, but as long as time travel remains theoretical, the retroactive suicide paradox serves as a warning about the dangers of manipulating the past. A man discovers a way to travel back in time. He does not want to change history. He only wants to observe the past. He sets his machine for the distant past, long before humans existed, and arrives in a prehistoric jungle. The world looks untouched, filled with plants and creatures that have not been seen for millions of years. He takes careful steps, knowing that even the smallest change might matter. But as he moves through the thick undergrowth, he steps on a butterfly. He barely notices. It is small, fragile, and insignificant to him. Satisfied with his journey, he returns to his own time. The world he left is gone. The cities he knew are different. The language is unrecognizable. The people do not look familiar. Somehow, stepping on that butterfly caused massive changes. It set off a chain of events, shifting history in ways he never expected. This idea is called the butterfly effect. It comes from chaos theory, which studies how small changes can grow into major consequences. The phrase comes from the idea that a butterfly flapping its wings in one part of the world might lead to a storm in another. The effect is not about the butterfly itself, but about how small actions lead to bigger ones, changing the course of events. Time travel stories often use the butterfly effect to show how delicate the past can be. Even a minor change might ripple forward, altering everything. The idea is simple. If you change one detail in history, even one that seems unimportant, it can completely reshape the present and future. Imagine a traveler who goes back to the 1800s and gives someone a modern tool. The person who receives it becomes wealthy by using technology no one else has. That wealth gives them power. That power changes who they marry, how their children are raised, and what businesses succeed. Over time, the world shifts in ways the traveler never expected. When they return to their own time, they find a world that is unrecognizable. That one gift set off a series of changes, leading to a future that never would have existed otherwise. Another example comes from sports. Suppose a fan travels back to the past and shouts a warning to a baseball player about an incoming pitch. The player reacts differently, hitting the ball when they would have missed it. That changes the outcome of the game. The team that was supposed to lose now wins. That changes who makes it to the championships. That shift affects sponsorships, team contracts, and future drafts. A small moment, a single sentence, reshapes the careers of players, the history of the sport, and the lives of people who would have never known that moment happened. Sometimes, the changes are accidental. A scientist goes back in time and simply breathes in bacteria that no longer exist in their own era. Those bacteria stay in their body when they return to the future. Without realizing it, they spread a disease that had been wiped out long ago. What seemed like a harmless trip to the past becomes a disaster for the future. Other times, the changes happen through indirect actions. A traveler leaves behind a single object that should not exist in that time period. A simple coin, a photograph, or a piece of paper. Someone in the past finds it, wonders about it, and starts making decisions based on that object. Maybe an inventor sees a modern device and spends years trying to recreate it, leading to faster technological progress. Maybe a historian finds evidence of something that should not exist yet, leading to confusion and doubt about the past. One small mistake can shift entire fields of knowledge. The butterfly effect is not only about negative changes. A small event can improve the future as well. If a traveler saves a single person from an accident, that person might go on to make a discovery that helps millions. If they encourage someone at just the right moment, that person might take a path they never would have considered. The effect works both ways. A small action can make the world worse or better. The problem is that it is impossible to predict which way it will go. That is why time travel stories often treat the past as something delicate, something that should not be touched. In many stories, travelers try to avoid the butterfly effect by being extremely careful. They move through history as if they are ghosts, making sure not to disturb anything. But even observation can change the past. Suppose a traveler watches a historical event, standing unnoticed in the crowd. Their presence still takes up space. A person who would have stood in that spot now stands somewhere else. That shift, as tiny as it seems, might be enough to set off a chain reaction. Some versions of time travel try to avoid this paradox by suggesting that history corrects itself. In these stories, small changes do not matter because the timeline heals itself, always leading back to the same outcome. For example, if a traveler stops a historical figure from dying, something else will happen that causes their death another way. This theory, sometimes called temporal resilience, suggests that some events are too important to change, no matter how much someone interferes. But if the butterfly effect holds true, no event is immune to change. There are also stories where travelers try to use the butterfly effect on purpose. A person from the future might want to reshape history for their benefit. They could go back in time and influence key events, hoping to create a world where they hold more power. But because the butterfly effect is unpredictable, their attempts might not go as planned. They might make one small change, expecting a certain result, but instead, the world evolves in a completely different direction. The butterfly effect highlights the biggest problem with time travel. It is impossible to know what changes will matter. A single word, a single step, or a single moment can alter history in ways no one can predict. Even if someone tries to be careful, the smallest action can ripple outward, affecting events in ways they never intended. That is why so many time travel stories end with travelers realizing that they cannot fix their mistakes. The past is too fragile. Once they change something, they can never put it back exactly as it was. Some argue that the butterfly effect is not just a theory of time travel, but also a reflection of real life. Every day, people make small choices that shape the future. A kind word at the right moment might encourage someone to pursue their dreams. A missed opportunity might lead to a completely different career. A single decision might set off a chain of events that changes everything. Time travel only exaggerates this idea, showing how even the smallest actions can have consequences that no one can predict. If time travel were real, controlling the butterfly effect would be nearly impossible. The moment someone stepped into the past, they would change it. Even if they did nothing, their mere presence would alter something. A breath, a movement, or an unnoticed action might be enough to reshape history. That is why many theories suggest that if time travel were possible, it would come with risks too great to manage. The past is not just a record of what happened. It is a complex web of interconnected events, each one influencing the next. If even the smallest change can alter everything, then time travel might be more dangerous than it is useful. A time traveler decides to go back to 1920s Germany with a single goal: kill Adolf Hitler before he rises to power. They believe that by eliminating him early, they can prevent World War II and all the suffering that came with it. They set their time machine, step out into the past, and track down Hitler before he ever becomes a figure of historical significance. They succeed. But then a problem arises. If Hitler never rose to power, World War II never happened. If World War II never happened, then there was no reason for anyone in the future to think about going back in time to kill him. This creates a paradox. The moment Hitler is removed from history, the events that led to the time traveler deciding to assassinate him also vanish. If there is no World War II, then there is no motivation for a future person to build a time machine and come back in time to prevent it. Without that motivation, they never step into the time machine in the first place. If they never step into the time machine, then Hitler is never killed in the past. But if Hitler is never killed, history unfolds just as it originally did, leading back to the moment where the time traveler decides to go back and kill him. The cycle repeats, creating an impossible loop. This is the core of the Hitler paradox, sometimes called the killing Hitler paradox. It highlights the contradictions that arise when someone tries to change the past in a way that erases their own reason for doing so. Time travel stories often rely on cause and effect. A person acts, and their actions shape the future. But in this paradox, the very act of changing the past eliminates the cause for the change. If the future changes in response to the time traveler's action, then the action itself becomes unnecessary and logically impossible. Imagine a slightly different version of the story. A scientist in the year 2050 invents a time machine after years of research, funded by governments that see time travel as the key to fixing historical mistakes. The first mission is simple: stop Hitler. The scientist gathers intelligence on Hitler's early years, learns where he lived, and calculates the exact point in time that would be most effective for intervention. The scientist steps into the machine and arrives in 1923, right before Hitler's failed beer hall putsch. The mission is a success. The scientist assassinates Hitler, ensuring that he never goes on to seize power. Back in 2050, the world changes. There was no World War II. The Holocaust never happened. The entire history of the 20th century unfolds differently. But this means the scientists' world, the world where they grew up, learned about Hitler, and built a time machine to stop him, no longer exists. With no Hitler in history, no World War II, and no destruction caused by the Nazis, there was never a reason to invest in time travel. The scientist's mission vanishes from history along with Hitler. But if the scientist never existed to travel back in time, then nobody went back to kill Hitler, which means history remains unchanged. And if history remains unchanged, then Hitler comes to power and starts World War II. This brings us back to the original situation, where the scientist is motivated to invent time travel and go back in time to stop Hitler. The cycle repeats. One possible way around this paradox is the idea that history is self-correcting. If someone goes back in time and tries to change a major historical event, the timeline finds a way to restore itself. Maybe the time traveler succeeds in killing Hitler, but another person steps up and leads Germany into a similar war. Maybe the war happens anyway, just with different leaders and slightly altered events. The outcome, global conflict, devastation, and massive loss of life, still occurs, just in a slightly different form. This would mean that no matter how much someone tries to change the past, history bends back toward the same general course. Another possible solution involves parallel universes. Instead of creating a paradox, killing Hitler simply creates a new timeline, one where he never existed. But the original timeline, where Hitler rose to power and World War II happened, still exists in a separate reality. In this view, the time traveler doesn't erase the reason for their mission. They just move into a different version of history. The problem with this explanation is that it doesn't solve the paradox. It avoids it by changing the rules of time travel. Instead of altering a single, consistent timeline, it assumes that every action creates a new branching path. A different approach suggests that history is fixed, and no matter what a time traveler does, they can't actually change the past in any meaningful way. If they try to kill Hitler, something always stops them. Maybe their gun jams, or they get arrested before they can carry out the act. Maybe they end up accidentally inspiring Hitler to become more careful, making his rise to power even more certain. This aligns with the concept of the Novikov self-consistency principle, which argues that if time travel is possible, events must always be internally consistent. Any attempt to change the past simply becomes part of history. A time traveler might not even realize they are part of the loop. They might believe they are making a change, but in reality, they are fulfilling history as it was always meant to happen. Maybe their actions are the very reason Hitler becomes the person he is. Perhaps a time traveler, in trying to kill Hitler, only manages to push events in a direction that ensures his rise to power. If they had never gone back in time, history might have unfolded differently, with a less extreme leader taking over instead. This paradox also highlights a deeper issue with time travel. What counts as changing history? Killing Hitler seems like a clear change, but history is a web of interconnected events. If the time traveler only removes Hitler without addressing the political and social conditions that led to his rise, does anything really change? Maybe another extremist takes his place. Maybe Germany still finds itself in a position where war becomes inevitable. Maybe a new conflict arises that is even worse than the one the time traveler tried to prevent. If the past is malleable, then the paradox suggests that changing it erases the motivation for the change. If the past is fixed, then time travel cannot alter it in any significant way. If parallel universes exist, then changing the past does not rewrite history, but instead creates a new one. Each interpretation has its own complications. The Hitler paradox forces us to think about whether time is something we can manipulate, or if it follows its own logic that prevents such contradictions from ever occurring. Stephen Hawking proposed the chronology protection conjecture as a way to explain why time travel to the past might be impossible. His idea suggests that the laws of physics prevent any changes to the timeline that could create contradictions. If time travel were possible, paradoxes like the grandfather paradox or the bootstrap paradox could arise. Hawking believed that the universe naturally prevents these problems by making time travel either physically impossible or so unstable that it collapses before it can happen. A simple way to think about this idea is to imagine a person who builds a time machine. They step inside and set the machine to take them back 50 years. If they arrive in the past and do something that prevents themselves from ever being born, they would not exist in the future to build the machine. This contradiction suggests that something must stop them from making the trip in the first place. The chronology protection conjecture proposes that time travel to the past is either forbidden by nature or that any attempt to change history fails for reasons built into physics itself. One possible way this could happen involves quantum mechanics. When people talk about time travel, they often imagine it as a smooth, logical process, like walking through a door and ending up in another time. But the laws of physics, especially quantum mechanics, do not always work that way. In many cases, physical systems behave unpredictably at very small scales. If time travel requires manipulating space and time at this level, small effects could grow so quickly that they prevent the process from ever being completed. This means a time machine, even if it could be built, might never actually work as intended. Another possible explanation comes from general relativity. Einstein's equations suggest that space and time can be warped under extreme conditions, such as near black holes. Some solutions to these equations suggest that closed time-like curves could exist, meaning paths through space-time that loop back on themselves. These loops would allow someone to travel to the past and interact with their own history. However, if such curves could exist, they might lead to instability. Any disturbance, no matter how small, could cause the entire system to collapse before anyone could use it. If this happens in every case, it would mean that nature has a built-in defense against time travel. Hawking supported his idea by considering what happens when you try to create a situation where time travel could occur. One possibility involves using a wormhole, a shortcut through space-time that could, in theory, connect two different points in time. If someone builds a wormhole and tries to turn it into a time machine, something strange happens. According to calculations, as soon as the wormhole is opened for time travel, quantum effects begin to build up inside it. These effects grow stronger and stronger until they destroy the wormhole before anyone can use it. This result suggests that even if someone finds a way to create a time machine, nature will prevent it from working. A practical way to imagine this is to think about trying to balance a pencil on its tip. In theory, if the conditions are perfect, the pencil could stay balanced forever. But in reality, small vibrations, air movements, or even tiny atomic shifts will eventually cause it to fall. The same principle might apply to time travel. Even if a time machine could be built in theory, small disturbances, perhaps even down to the level of quantum fluctuations, would destroy it before it could be used. Hawking also looked at the idea of energy buildup. If time travel were possible, it could lead to situations where energy accumulates without limit. Imagine a beam of light that enters a time machine, loops through time, and then re-enters the machine over and over. If the machine allows infinite loops, the energy of the light beam could increase endlessly, leading to an explosion or some other destructive event. This kind of feedback loop suggests that time machines might be impossible simply because they cannot sustain themselves under the laws of physics. Another way to look at this is through entropy, which is a measure of disorder in a system. In normal situations, entropy increases over time. Ice melts into water, wood burns into ash, and stars eventually burn out. If time travel to the past were possible, it could lead to violations of this rule. A time machine might allow energy and matter to move backward in time, decreasing entropy instead of increasing it. Since all known physical processes follow the rule that entropy increases, time travel might be impossible because it would contradict the fundamental direction of time itself. The chronology protection conjecture does not say that time travel is impossible in every sense. It only suggests that travel to the past is likely prevented by physical laws. Some physicists argue that time travel to the future is still possible based on relativity. For example, if someone moves at speeds close to the speed of light, time slows down for them relative to others. This means they could travel forward in time faster than people on Earth, but this type of time travel does not create paradoxes. Hawking's conjecture leaves open the possibility that if time travel is ever discovered, it will have built-in safeguards. These safeguards could make sure that paradoxes never arise. Some theories suggest that even if someone could travel to the past, they would always be prevented from making any changes that affect the present. This idea, known as the Novikov self-consistency principle, suggests that history is fixed, and any attempt to change it simply leads to events that ensure the timeline remains intact. An example of this would be a time traveler who goes back to prevent a famous historical event. Every action they take ends up playing a role in making sure the event still happens. If they try to warn someone, their warning might be misunderstood. If they try to interfere, their interference might be the cause of the event. In this way, history protects itself, and paradoxes never arise. Hawking's idea suggests that the universe has mechanisms in place to prevent situations where time travel could lead to contradictions. Whether these mechanisms come from quantum mechanics, relativity, or entropy, they all seem to point in the same direction. The past cannot be changed, and attempts to do so will always be blocked by natural laws. This idea aligns with what we observe in physics. While theoretical models sometimes allow for time loops, actual experiments have never shown any evidence that backward time travel is possible. One interesting question is whether advanced civilizations, if they exist, have already discovered this limitation. If aliens had developed time travel, would we see evidence of them visiting the past? Some scientists argue that the lack of such evidence supports the chronology protection conjecture. If time travel to the past were possible, it would be reasonable to expect that future civilizations might use it. Since we do not see any signs of time travelers, this could mean that time travel is fundamentally impossible. The chronology protection conjecture remains one of the strongest arguments against time travel. Instead of relying on specific technology or engineering limits, it suggests that time travel is prevented by nature itself. Whether through quantum instability, energy buildup, or entropy, the universe may have ways of ensuring that paradoxes never occur. Hawking's idea offers a simple explanation for why time travel stories remain in science fiction rather than reality. A billiard ball sits on a smooth table. A player lines up their shot, strikes the cue ball, and sends it toward a cushion. The ball follows the expected path, bouncing off the edges before coming to a stop. Now imagine a different scenario where the ball not only moves across the table, but also moves through time. It rolls forward, strikes a wall, and vanishes into a wormhole, reappearing in the past a few seconds earlier. That same ball is now on the table again, but something strange happens. As it moves toward the wormhole, it collides with itself, its own past version, before it can enter, knocking itself off course. If that happens, the ball never enters the wormhole, meaning it never traveled back in time. But if it never traveled back, how did it collide with itself? This is the problem raised by Polchinski's paradox. A time traveler might picture wormholes as tunnels through space and time. The idea is that something could enter at one end and exit at the other, arriving at a different point in the past. This paradox assumes a wormhole exists where a billiard ball can enter, travel back a few seconds, and exit before its original path was complete. In theory, this should create a simple time loop. The problem appears when the ball's own actions interfere with that loop. If the ball in the past is pushed away, it never enters the wormhole in the first place. That breaks the loop and causes a contradiction. Physicist Joseph Polchinski proposed this paradox as a way to test time travel rules in physics. Some solutions in general relativity suggest time loops, known as closed time-like curves, could be possible. If they exist, objects might be able to move through them, much like the billiard ball. But physics follows a strict rule called causality. Cause comes before effect. A knocked-off course billiard ball shouldn't appear in the past if it never originally traveled through the wormhole. This paradox challenges the idea that time travel could work without creating logical inconsistencies. A key problem here is self-interaction. The ball interferes with its own past, making changes that should prevent its future path. This is similar to the grandfather paradox, but removes human decisions from the equation. It's easy to imagine a person choosing to avoid certain actions, but a billiard ball follows physics. It moves according to velocity, momentum, and collisions. If an object following these laws enters a wormhole, there should be a way to track its movement without contradictions. But Polchinski's setup creates a loop that seems impossible to resolve. One possible answer comes from Novikov's self-consistency principle. This principle says that if time travel is possible, events must always be consistent with themselves. The billiard ball cannot create a paradox because physics will not allow it. Instead of knocking itself completely off course, the past version of the ball might receive only a slight nudge. That small change means the ball still enters the wormhole, but at a slightly different angle. This way, the loop remains unbroken and no contradiction appears. The ball's motion adjusts in a way that ensures time remains consistent. Think about how this might look in action. A ball rolls toward the wormhole, enters, and reappears in the past. Instead of colliding with itself and preventing entry, it grazes the past version, altering its angle slightly. The difference is small, but it's enough to make the path self-consistent. The ball still enters the wormhole, but its motion has changed just enough to allow for a continuous loop without paradoxes. This keeps physics intact. Some scientists suggest that this kind of adjustment might apply to all time travel situations. If past and future interact, they must do so in ways that don't break causality. The idea is that time travelers, objects, or information cannot alter the past in ways that prevent their original journey. Every event must fit together logically. This could mean that paradoxes only seem possible because of missing information. Given the right conditions, every event might resolve in a way that prevents contradictions. There's another perspective that relies on quantum mechanics. Some physicists propose that if time travel changes the past, it might create alternate timelines instead of paradoxes. The billiard ball that gets knocked off course would enter a different timeline, separate from its original one. This avoids contradiction because each timeline remains internally consistent. The original billiard ball still enters the wormhole in one timeline, while the altered ball exists in another. This view suggests that time travel does not affect a single continuous history, but instead branches into multiple realities. If wormholes do exist, they could offer a method of time travel without breaking physics. But the presence of paradoxes like this one raises concerns about how they might function. Would physics prevent such paradoxes naturally, as Novikov's principle suggests? Or would time travel require new laws beyond our current understanding? The billiard ball scenario is simple, but the implications stretch far beyond the table. The question remains, if something can interact with its own past, what rules ensure it doesn't break causality? The billiard ball paradox offers a mechanical way to explore these issues. Unlike human decisions, which involve free will and choice, the ball follows only the laws of motion. If a simple object like this creates a paradox, what does that say about more complex time travel scenarios? Would a time traveler arriving in the past automatically take actions that preserve history, even without meaning to? Or would the universe prevent certain events entirely? Understanding this paradox requires thinking about physics in a way that connects time and motion. Normally, cause leads to effect in a clear direction. If time loops are possible, that order becomes less clear. The billiard ball must somehow move in a way that keeps its own history intact, whether that means slight changes, new timelines, or a deeper principle we don't yet understand. The problem remains an important test for any theory of time travel. Polchinski's paradox highlights the difficulties in allowing objects to interact with their past selves. If time travel is possible, events must fit together in a way that prevents contradictions. The paradox challenges scientists to explain how time loops might work while keeping causality intact. Whether through self-consistency, alternate timelines, or yet undiscovered principles, any successful time travel theory must resolve these kinds of conflicts. A man steps into a time machine and sets it to travel to the past. The machine activates, and in an instant, he disappears from his original timeline. Where does he arrive? If time travel follows the principles of classical physics, he should appear in a single, definite past, interacting with a world that unfolds in a predictable way. But if quantum mechanics governs time travel, things become more complicated. The man might exist in multiple pasts at once, with different versions of events unfolding in parallel. His journey doesn't lead him to a single past, but to a cloud of possibilities where his actions create different outcomes simultaneously. Quantum mechanics describes the world at its smallest scales, where particles do not have fixed positions until they are measured. Instead, they exist in a superposition of states, meaning they occupy many possible positions at once. If a time traveler were subject to the same principles, he might arrive in a past that is not singular and fixed, but instead made up of overlapping probabilities. This idea follows from the famous Schrödinger's cat thought experiment. In that scenario, a cat inside a sealed box exists in a superposition of both alive and dead states until someone observes it. The observer's measurement forces the cat into one definite state. If a time traveler moves through time like a quantum particle, then he too might exist in multiple possible pasts until something collapses his state into one specific timeline. Imagine a woman who builds a time machine. She decides to test it by traveling to the year 1900. When she activates the machine, she expects to land in a world identical to what history books describe. But when she arrives, she finds two versions of the past unfolding around her. In one version, people recognize her and seem to anticipate her arrival, as if she had already been there before. In the other, no one reacts to her presence, and she appears as a complete stranger. She tries to interact with both versions of reality, but each time she focuses on one, the other fades from view. She is caught in a superposition of pasts, unable to determine which one is real. Only when she makes a crucial decision, perhaps speaking to a particular person or altering an event, does one past solidify and the other vanish. This raises a deeper question. If the past exists in multiple states, what determines which one becomes real? In quantum mechanics, a measurement forces a system to take on a definite value. If a time traveler's presence acts as a kind of measurement, then his mere arrival in the past might determine which version of history becomes fixed. But what happens before that point? Does history exist in a blurred, uncertain state, waiting for the traveler to make a choice? If so, the past is not a static record, but a shifting set of possibilities influenced by the traveler's actions. A man decides to travel to the past to prevent a disaster. He knows that a fire will destroy an important library in the year 1800, so he sets his machine to arrive the day before. As he steps out, he sees the building still intact. He rushes inside to warn the librarians, but as soon as he speaks, the scene around him wavers, and suddenly he is outside the building, watching it burn. Confused, he tries again. This time, he doesn't speak, but instead runs to the nearest fire station. The moment he reaches the firefighters, the fire disappears, and he finds himself back inside the intact library. It's as if his presence is shifting between two versions of history, one where the fire happens and one where it doesn't. His attempt to change the past doesn't work in the usual way. Instead of choosing one reality over another, he seems to exist in both until something forces a collapse into a single outcome. This paradox challenges the idea that history is a fixed sequence of events. Instead, it suggests that the past is as uncertain as the future, at least until an observer forces it to take on a definite form. If true, this means that time travelers do not move through a rigid timeline, but instead interact with a probability cloud of possible histories. Their actions don't just change the past, they define which past actually existed. The implications extend beyond time travel. If the past can exist in multiple states, then memory and records become unreliable. A traveler who returns from a journey to the past might find that history books no longer describe the events he remembers. Two people who visit the same past might return with different memories of what happened. The past, rather than being a shared reality, becomes subjective, dependent on who interacts with it and how. This idea resembles the quantum measurement problem, where a particle's state depends on how it is observed. In this case, history itself depends on how and when it is visited. A woman attempts an experiment. She writes a letter warning a scientist in the year 1700 about an upcoming war. She places the letter in a secure time capsule and then travels to the past herself to see if the scientist receives it. When she arrives, she finds the letter sitting on his desk, untouched. Puzzled, she picks it up, only to see the text fade before her eyes. In that moment, she remembers that she never actually wrote the letter. She only planned to. The moment she interacts with it, history rearranges itself to match what she truly did. The act of observation has reshaped the past. This suggests that time travel is not simply about moving through time. It involves interacting with time as if it were a quantum system. Just as a particle exists in multiple states until measured, the past exists in multiple forms until a traveler's actions force it into a single version. This would explain why time travel paradoxes arise. If a traveler kills their grandfather, they don't erase their own existence immediately. Instead, they create a split in historical probabilities, where both realities exist until something forces a resolution. In some cases, this resolution might prevent paradoxes by ensuring that the traveler always arrives in a version of the past where their actions make sense. In others, it might lead to contradictions, where two versions of history struggle to coexist. A man invents a time machine and wonders if he can use it to meet himself in the past. He sets the machine to take him back 5 years and steps inside. As he arrives, he expects to see his younger self in the room. But to his surprise, the room is empty. He waits, but no one appears. Confused, he checks his old records. They still show that he lived in this place 5 years ago. If he was here, why can't he see himself? Then he notices something strange. Every time he looks away from a mirror, he catches glimpses of his younger self reflected in the glass. But when he turns to face it directly, the reflection vanishes. It's as if his past self exists only in a probability state, appearing only when not directly observed. This version of time travel introduces a new layer of uncertainty. Instead of assuming that the past is a single, fixed reality, it treats history as something fluid, affected by observation and interaction. If quantum mechanics governs time travel, then history does not exist in a definite form until something or someone forces it into place. A time traveler does not simply visit the past, they shape it by their presence. This means that every journey into the past is not just a trip through time, but an act of defining reality itself. A man steps into a time machine, determined to change a moment in history. His goal is simple: prevent a terrible event from happening. He sets the machine to the exact moment in time where he believes he can make a difference. When he arrives, he takes action, making sure the event never occurs. He expects to return to his time and see the world transformed. But when he activates the machine and returns to the future, nothing has changed. The world he left behind remains the same. Confused, he wonders what went wrong. Did his actions fail to make an impact, or did something else happen? The idea that changing the past might not affect the present you came from is central to the parallel universe paradox. Instead of altering the existing timeline, your actions create a new one. The past you traveled to no longer leads to your original future. It branches off into an entirely different reality. You may have saved the world in that timeline, but your own world remains unchanged. This paradox raises a fundamental question. What happens to the traveler? Do they return to the same timeline they left, or do they become part of the new one? A traveler could go back to stop a historical disaster, believing they have erased it from history. But when they attempt to return, they find themselves in a version of the future where the event never happened, yet it is not their own time. Their past experiences, their memories, and everything they knew before stepping into the machine still exist elsewhere, in a different timeline. They are now stranded in a world that feels unfamiliar. The people look the same, the cities have the same names, but details are off. Perhaps someone they once knew no longer exists, or technology has developed in an unexpected way. The traveler begins to realize that their actions did not rewrite history, but instead created an alternate version of it. This paradox suggests that every choice creates a branching path. If someone could travel back and change an event, they would not be overwriting reality, but creating a split. The original timeline continues as if nothing changed, while a new one grows from the moment of interference. This concept aligns with the many worlds interpretation of quantum mechanics, which proposes that every possible outcome of an event exists in a separate universe. In this view, time travel does not violate causality because it never disrupts an existing timeline. It simply creates another. Consider another scenario. A scientist working on time travel manages to send a message to the past. The message warns an earlier version of themselves about a mistake they are about to make. The past scientist, acting on the information, avoids the error. In their reality, the mistake never happens. But what happens to the timeline where the mistake did occur? If the message was sent from a future where the error existed, does that future still remain? Or does it split, leaving one reality where the message was never needed and another where it was sent? Some theories propose that if parallel universes exist, a time traveler would have no control over which version of history they end up in. If every change creates a branch, then every trip to the past results in a different version of events. This makes time travel unpredictable. A person could attempt to return home only to find that they have landed in yet another alternate reality. Even small changes could create drastic differences over time. The idea of a traveler repeatedly jumping from one version of history to another introduces an unsettling possibility. They may never find their way back to their original timeline. Another unsettling question is whether the traveler themselves is duplicated. If changing history creates a new timeline, does the original traveler still exist in the timeline they left? If so, does that mean there are now two versions of the same person? One who continued in the unchanged timeline and another who lives in the new one. If a traveler prevents their own birth in an alternate reality, does it affect them at all? Or does it only apply to the version of history they altered? The parallel universe paradox challenges the idea that the past can be rewritten in the way we usually imagine. Instead of a single timeline being erased and replaced, each change creates a new reality that exists alongside the old one. This avoids the contradictions found in other time travel paradoxes, such as the grandfather paradox, because it does not allow a traveler to erase their own existence. But it also introduces a new kind of uncertainty. If every change spawns a new world, then time travelers might never truly correct their own history. They would only create alternate versions where different outcomes occur. Imagine a woman who travels back to stop a war. She intervenes at a critical moment, preventing key events that would have led to conflict. When she returns, she expects to see a peaceful world. Instead, she finds herself in a version of history where the war never happened, but it is not her world. The people she knew, the life she had before she stepped into the machine, are gone. She has changed history, but only in a world separate from the one she came from. The war still happened in her original timeline, and nothing she did can change that. This concept extends to personal decisions as well. Suppose a man regrets a choice he made years ago. He travels back to fix it, thinking that by making a different decision, he will return to a better future. He changes his actions and jumps forward again, but he does not find himself in a better version of his life. Instead, he has arrived in a different version of history, one where his original mistake never happened, but also one where he never lived the same experiences. His past self in the original timeline still made the mistake, and that version of history continues as if he had never left. If parallel universes exist, then time travel might not allow people to change their own past, but only to create variations of it. This raises questions about identity and continuity. If a person creates a new reality, are they still the same person? If they succeed in making a better world but can never return to their own, does their journey matter? And if infinite alternate timelines exist, does anything ever truly change? The paradox does not rely on contradictions like other time travel dilemmas. It offers a solution to problems like causality loops and paradoxical self-erasure by proposing that nothing is erased, only expanded. Yet it creates new challenges. It suggests that travelers can never truly fix their pasts, only branch into different versions of events. This means that attempts to change history are not really about undoing mistakes, but about creating separate worlds where those mistakes never happened. A person who steps into a time machine believing they can rewrite their own story may find themselves in an unfamiliar reality, wondering whether they have truly changed anything at all. A person discovers a way to travel between parallel universes. They wonder if they can use this ability to make themselves rich. The idea is simple. They buy a lottery ticket in their own universe. Then, before the winning numbers are announced, they jump to another universe where the same lottery exists, but where they know the winning numbers in advance. They buy a ticket in that universe with the correct numbers, wait for the results, and become an instant millionaire. It sounds foolproof. If there are infinite universes, one of them must have the right combination of circumstances where they win. But does it really work that way? The first issue is whether these universes are truly separate or if they are somehow connected. If they are separate, Each version of the person exists independently, and jumping between them does not affect the others. That would mean a version of them in their original universe still loses the lottery, while another version in the winning universe suddenly acquires an incredible amount of wealth. The question then becomes whether the original version actually benefits or if they just become a different version of themselves with a different outcome. If the universes are connected in some way, there might be other problems. If a person keeps switching timelines until they win, they are effectively trying to force a specific outcome. This assumes that a version of them must win somewhere and that they can freely move into that winning reality. But what if reality does not work that way? What if every time they jump, they create new possibilities instead of selecting from existing ones? That would mean that no matter how many jumps they make, the result is still uncertain. Another complication is whether the act of jumping itself changes the timeline. Suppose they enter a universe where they are about to win, but their arrival alters a small detail. Maybe they distract someone at the lottery office, or maybe the presence of an extra version of themselves causes a different observer effect. In that case, they may have arrived in a winning timeline, but by being there, they no longer win. Even if they could find a way around that problem, there is still the issue of practical application. Most lotteries do not simply hand out millions of dollars the moment someone wins. There are taxes, verification processes, and waiting periods. A sudden appearance of a person without a clear history in that universe might raise suspicion. Their personal records, bank accounts, and identification might not exist in this new timeline, meaning they have no legal claim to the winnings. There is also a moral consideration. If they assume that every universe is real and that every version of themselves is an actual person, then what happens when they take over the life of a winning version? That version of them might have lived through struggles and experiences that led to their success. If an outsider version enters and takes over, it is essentially stealing from themselves. Even if they do not actively replace another version, the mere act of jumping into that reality might change it enough to deny that version their win. A different angle is whether an infinite number of universes guarantees an outcome. In theory, if there are infinite universes, then every possible scenario must happen somewhere. But that assumes a specific structure of reality. Not all theories of the multiverse agree on how these universes exist. Some suggest that not every possibility is realized, only those that follow a consistent path of probability. If that is true, there may be universes where they win, but those universes might be unreachable because their decisions have already determined a different set of outcomes. The act of choosing a timeline is also unclear. If a person could truly navigate the multiverse, how would they determine which universe to enter? If they are simply jumping at random, they might never find the right one. Even if they could pick a specific reality, that assumes they can control it to a degree that allows them to land exactly where they need to be. If they miss by even a small fraction, they might enter a universe where someone else wins, or where the winning numbers are different, or where the lottery does not even exist. Another potential problem is whether the concept of identity remains stable across timelines. If every universe has a different version of them, and they move into a version that is not their own, are they still the same person? If their consciousness replaces the version in that universe, then their original self ceases to exist in the previous one. If instead they merge with the version in the new universe, their thoughts and memories might not be the same. That raises the question of whether they truly benefit from winning, or if they simply cease to be who they originally were. There is also the matter of causality. If they believe they can jump into a universe where they win, then logically, that universe must have existed before they made the choice. But if they only made the choice after seeing the numbers in their original timeline, then their decision must somehow retroactively create a universe where they have already won. That creates a paradox where their actions depend on an outcome that was not initially available to them. Even if they assume the multiverse allows all possibilities, it does not necessarily mean they have the ability to access them. If they cannot choose where they end up, then no matter how many times they jump, they may never find the version where they win. They may instead find versions where they almost win, or where they miss by one number, or where the jackpot is split among many people, reducing the payout. The nature of probability also complicates the idea. Winning the lottery is already an event with extremely low odds. The assumption that there must be a universe where they win suggests that every improbable event must occur somewhere. But probability does not guarantee that every event happens, only that it has a chance. If the multiverse follows probabilistic rules rather than deterministic ones, then a winning universe may not necessarily exist. Another consideration is whether their ability to jump between universes is subject to rules. If there are laws of physics governing these jumps, they may not be able to select universes based on specific criteria. Instead, they may be subject to a form of randomness or limited access to certain timelines. If they cannot control where they go, then the strategy of picking a winning timeline becomes unworkable. If their movement between universes is unrestricted, then they could theoretically do more than just win the lottery. They could enter a universe where they are already rich, or where they were born into extreme wealth, making the lottery unnecessary. But if such a universe exists and is accessible, then it raises further questions about whether they are truly changing their fate or simply stepping into a different version of reality, where another version of them already lived that fate. The very premise of the paradox assumes that reality allows for such manipulation. If reality does not work that way, then no amount of jumping through universes would allow them to pick the one they want. They may only ever observe possibilities without being able to directly alter their own circumstances. In that case, the idea of using the multiverse to win the lottery is not just impractical but impossible, no matter how many versions of reality exist. The universe is vast and full of mysteries, but one of the biggest puzzles in cosmology is why it looks so uniform. When scientists observe space in all directions, they see that the temperature of the cosmic microwave background, the faint radiation left over from the Big Bang, is almost the same everywhere. This is strange because, given the vast size of the universe, different regions should not have had time to interact and equalize their temperatures. This problem is known as the horizon problem. The horizon problem arises from the limits of how fast information can travel. In our universe, the speed of light is the ultimate speed limit. If two regions of space are too far apart, light from one cannot reach the other, meaning they cannot exchange energy or influence each other. According to standard cosmology, the early universe expanded rapidly after the Big Bang. Because of this rapid expansion, some regions of the universe that we observe today should never have been in contact with one another. Yet, when scientists measure the cosmic microwave background, they see a nearly identical temperature everywhere. This suggests that these distant regions somehow managed to reach thermal equilibrium, even though under normal physics, they should not have had enough time to do so. One explanation for this problem is cosmic inflation. This theory suggests that, in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light. This rapid expansion could have stretched out any irregularities and ensured that all regions started from the same conditions before they became separated by enormous distances. Inflation is widely accepted among physicists, but it remains a theoretical concept. There is no direct evidence of how or why inflation started or stopped. Time travel introduces another way to think about this problem. If information or matter could move backward in time, it might explain how distant regions of the universe managed to balance their temperatures despite being beyond each other's communication range. Suppose a mechanism allowed energy or radiation to travel back in time, reaching areas that should have been too far apart to interact. This could provide an alternative way for the universe to achieve the uniformity we observe today. To understand how time travel might work in this context, consider a simple analogy. Imagine a large room filled with air. If the air is not mixed well, some areas will feel warmer than others. If you open a door between two sections, the warm air will move into the cooler area, and over time, the temperature will balance out. This happens because molecules carry energy from one place to another. But what if these sections were permanently separated? Under normal conditions, they would never reach the same temperature because there is no way for energy to pass between them. Now imagine that you could send air molecules backward in time. Even if the two sections of the room were separated, molecules from one side could travel into the past, cross into the other section before the barrier existed, and then continue forward in time. This would allow the two areas to exchange energy, balancing their temperatures despite never being in direct contact in the present. In the case of the early universe, something similar could have happened. If time travel were possible at a fundamental level, then energy, light, or even entire particles could have traveled backward in time and reached distant regions before they were separated by cosmic expansion. This would allow the universe to achieve the level of uniformity we see today, even without the need for inflation. Some theoretical physics models suggest that time travel is not entirely impossible. General relativity allows for solutions that include closed time-like curves, which are paths through space and time that loop back on themselves. These curves could, in theory, permit information or particles to travel into the past. While no practical method for time travel has been discovered, the equations of physics do not entirely rule it out. Another way to think about time travel's role in the horizon problem is through wormholes. A wormhole is a hypothetical tunnel that connects two points in spacetime. If wormholes existed in the early universe, they could have linked distant regions, allowing heat and energy to pass between them, even if those regions were too far apart to communicate under normal conditions. In this way, time travel via wormholes could have helped the universe reach thermal equilibrium before expansion carried these regions apart. One challenge with this idea is stability. Wormholes, if they exist, might collapse before they could allow significant energy transfer. Even if time travel were possible, there is no clear explanation for why it would only have occurred in the early universe and not in later stages of cosmic evolution. However, some physicists speculate that extreme conditions, such as those present shortly after the Big Bang, could have allowed exotic physics that no longer operates in the present-day universe. The possibility of time travel as an explanation for the horizon problem raises deeper questions about the nature of time itself. If time travel played a role in shaping the universe, it suggests that time might not be as rigid as it appears in everyday life. Instead of moving in only one direction, as human experience suggests, time might have more flexibility at the fundamental level of physics. If a future scientific breakthrough revealed that information or particles could travel backward in time, it would change our understanding of causality. In everyday life, causes precede effects. If time travel were real, effects could sometimes precede their causes, creating scenarios where events in the future influence the past. This would mean that the uniform temperature of the universe could be the result of energy transfer from a later stage in its history, rather than from an initial state imposed at the very beginning. A related question is whether time travel in this context would require a guiding mechanism. If particles or energy can move backward in time, what determines where they go? Do they travel randomly, or is there an underlying principle that directs them toward specific regions? If a natural process caused time-traveling energy to flow in a way that balanced the universe's temperature, it would imply that some form of self-regulating mechanism was at play. Although the horizon problem remains a major challenge in cosmology, time travel offers a unique way to approach the issue. If energy or radiation in the early universe could move through time, it could help explain why distant regions share the same temperature. While this idea is speculative, it highlights how unconventional solutions can sometimes provide insights into fundamental questions about the universe. Understanding whether time travel played a role in shaping the universe requires more research and better observations. Advances in physics, especially in areas like quantum mechanics and general relativity, may one day provide a clearer picture of how time functions on the largest and smallest scales. Until then, the horizon problem remains a mystery, and time travel remains one of the most intriguing possibilities for solving it. A black hole has an immense gravitational pull. It is so strong that nothing can escape once it crosses a certain point called the event horizon. Scientists believe that this extreme gravity could also affect time. In theory, a black hole might bend space and time in such a way that it allows travel to the past or future. This idea raises a question. If a black hole can enable time travel, does it create logical problems? To understand how a black hole might allow time travel, consider what happens when an object moves near one. As it gets closer, time slows down for that object compared to someone watching from a distance. This effect is known as time dilation, and it happens because gravity changes how time flows. If an astronaut approaches a black hole but avoids crossing the event horizon, they will experience time differently from people far away. When they return, they may find that many more years have passed for those who stayed behind. This type of time travel into the future is already predicted by physics and does not create paradoxes. Traveling into the past is where problems begin. Some scientists suggest that if a black hole rotates fast enough, it could create a tunnel in space-time called a wormhole. A wormhole might connect different points in time, allowing someone to enter at one moment and exit in the past. If this is possible, it leads to contradictions. A person could go back and prevent themselves from ever entering the wormhole. This would mean they never traveled in time, yet they did. This type of contradiction is a causality problem. Causality is the rule that cause comes before effect. If a black hole lets someone break this rule, it challenges how reality works. Imagine a scientist who receives a book about time travel from someone in the future. They study the book, build a time machine, and then send the same book back to their past self. The book appears to exist without anyone ever writing it. If a black hole allows backward time travel, situations like this could happen. Objects or information could loop endlessly in time with no clear beginning. Another problem with black hole time travel is stability. Wormholes may exist in theory, but they might not stay open long enough to allow travel. Some physicists suggest that tiny disturbances could cause the wormhole to collapse before anyone can use it. If this is true, nature may prevent paradoxes by making backward time travel impossible. Even if a black hole forms a stable wormhole, using it might require exotic matter with unusual properties. Scientists do not know if such matter exists. Some researchers propose that the universe protects itself from paradoxes. This idea, called the Chronology protection conjecture, suggests that physical laws prevent time loops from forming. If black holes create paths to the past, something might always happen to block them. A natural event, like radiation or quantum effects, could destroy any time machine before it works. If this idea is correct, black holes may bend time, but they cannot break causality. Another issue is information loss. A black hole pulls in everything, including light, and does not let it escape. If a person enters a black hole, their information may be lost forever. This leads to a paradox known as the black hole information paradox. If information disappears, it contradicts a fundamental rule in physics that says information cannot be destroyed. Some scientists think that information is not lost, but scrambled in a way we do not yet understand. If black holes allow time travel, they might also allow information to escape in unexpected ways. This raises more questions about how time and space behave under extreme conditions. Some theories suggest that a black hole could act as a one-way time machine. If someone falls in, they may reach a future point in time faster than anyone outside, but they can never return. This would allow travel forward, but not backward. This version of black hole time travel does not violate causality, since it prevents paradoxes. However, it is not useful as a time machine because the traveler cannot send messages back or change past events. A more extreme idea is that a black hole might connect to another universe. If this happens, entering a black hole might not lead to the past of our universe, but to a different reality. In that case, actions taken by a time traveler would not affect their original timeline, avoiding paradoxes. But there is no evidence that alternate universes exist or that black holes link to them. Black holes challenge our understanding of time. They show that time can stretch, slow, and possibly even loop. If black holes allow backward time travel, they could create logical contradictions. Scientists continue to study these questions, but for now, black holes remain a mystery. If time travel to the past is possible, why haven't we seen time travelers? This question is an extension of the Fermi paradox, which asks why, In a vast universe with billions of stars and planets, we don't see clear evidence of intelligent alien life. If time travel exists in the future, it stands to reason that someone at some point would have traveled back to our time or earlier. But history holds no records of visitors from the future. There are no undeniable artifacts, no strange sightings that can be verified beyond folklore, and no scientifically accepted reports of people appearing out of nowhere with knowledge of the future. This raises a question. If time travel is real, why does it seem like we are alone in time? One possibility is that time travel is simply not possible. The laws of physics, as we understand them, do not yet provide a clear method for traveling backward in time. While theories in general relativity suggest the existence of closed time-like curves, pathways that could, in theory, allow for movement through time, they remain speculative. There is no working model or experiment that proves backward time travel can occur. If time travel is impossible at the fundamental level, then of course we would never see visitors from the future. They cannot come back because the technology to do so will never exist. Another explanation is that time travel might be possible, but with severe limitations. It may be that traveling back in time is only possible to the point when the first time machine is built. If a time machine requires a stable wormhole, an exotic form of matter, or an advanced gravitational structure, then it may not allow access to points in history before the machine was created. This would mean that once humanity invents time travel, people in the future could only visit moments after that breakthrough, never before. If no time machine exists today, that would explain why we don't see time travelers. Some argue that time travelers could be visiting us, but they are undetectable. They might be disguising themselves as ordinary people, blending in to avoid disrupting history. If a person from the future arrives in the present, they may have strict rules about interference, much like modern scientists observing wildlife. They may not interact in any way that would change events, ensuring that history unfolds naturally. If they possess advanced technology, they might have ways of making themselves invisible or undetectable to human senses. If time travelers follow strict guidelines, it would make sense that we do not notice them. Another possibility is that time travelers do not find our era interesting enough to visit. If time travel exists in a distant future, those who possess it may have little reason to return to our time. They may be more interested in far more significant moments, either in the deep past or far into the future. They may also avoid times when technology is primitive compared to their own. A civilization capable of time travel might see us the same way we view ancient civilizations, interesting from a historical perspective, but not worth direct interaction. It is also possible that time travel creates alternate timelines, meaning that travelers never enter our own reality. If traveling to the past causes a new branch of history to form, then any visitor who arrives in a different time would never be part of our present. They would be in a separate timeline, one that does not affect us or leave traces in our reality. If this is true, then people in those alternate histories may see time travelers, but we never will. The idea of paradoxes may also prevent time travelers from coming to our time. The grandfather paradox suggests that if someone goes back in time and alters a crucial event, they might erase their own existence. If time travel is real, there may be a built-in mechanism that prevents changes to history. This could mean that anyone who attempts to visit the past is stopped by the nature of time itself. Events might correct themselves to prevent contradictions, keeping history on a fixed path. If this is the case, time travelers may be unable to reveal themselves or interact in a way that would let us know they exist. Some believe that time travelers have come, but their presence has been misinterpreted. Historical accounts of strange figures, unexplained knowledge, and technological leaps in the past have led to speculation that visitors from the future may have influenced certain events. Stories of people appearing mysteriously, possessing information ahead of their time, or disappearing without explanation often fuel theories about time travel. But none of these accounts provide concrete evidence. No confirmed case of a person from the future has ever been verified beyond anecdotal reports or speculation. Another potential reason we do not see time travelers is that they may be prevented from visiting the past by laws or ethical considerations. If time travel is discovered in the future, it is possible that governments or powerful organizations control access to it. If traveling to the past poses a risk to the stability of history, there may be strict regulations preventing its use. It is also possible that societies in the future have decided it is unethical to interfere with the past, much like we now have ethical debates about genetic modification, artificial intelligence, or human cloning. The choice to avoid disrupting history may keep time travelers from making themselves known. A more radical idea is that time travelers do not come to our era because humanity does not survive long enough to develop time travel. If civilizations tend to destroy themselves before reaching that level of technology, then there will never be future humans traveling back to visit us. This aligns with some interpretations of the Fermi paradox, which suggests that intelligent civilizations are rare because they do not last long enough to reach interstellar travel. If an advanced society collapses before mastering time travel, then time travelers from the future will never exist. Another possibility is that time travel does not work the way we imagine. Many fictional stories depict time travel as an instantaneous jump from one point to another. But if time travel requires moving through a complex process, such as traveling near a black hole or using a machine that takes centuries to function, then it may not be practical to use for historical visits. The process of reaching the past may be so difficult or resource-intensive that only a few people ever attempt it. If it requires vast amounts of energy, rare materials, or conditions that are nearly impossible to create, then the number of time travelers would be so small that we would never notice them. There is also the possibility that time travelers have tried to visit us but failed. If traveling to the past involves extreme dangers, such as exposure to high radiation, unstable wormholes, or unpredictable quantum effects, then most attempts may end in failure before reaching our time. If every trip back results in the traveler being lost, destroyed, or stuck in a time loop, then we would never encounter successful time travelers. The process itself may be so unreliable that it prevents consistent travel to the past. Some suggest that our perception of time is too limited to recognize time travelers. If someone from the future experiences time differently or exists in a state we cannot perceive, then they could be here without us realizing it. If they interact with the universe in a way that is beyond human understanding, then their presence might be invisible to us, just as certain wavelengths of light or types of energy are beyond our senses. The question of why we do not see time travelers remains unanswered. If time travel is real, there must be a reason why they do not reveal themselves. Whether the answer lies in physics, ethics, danger, or simple disinterest, the fact remains that history holds no clear evidence of visitors from the future. If they are out there, they are doing an excellent job of staying hidden.